All right. My Zoom window has disappeared, but hopefully, hopefully you all can see it. And thanks to everyone who made it out. I know you all had a late night last night, probably if you're in Italy. And if you're in the US, thanks for staying up. I want to start really quick by just thanking Matteo and Dan for putting this conference together, and of course all the staff and the chairs there who have made it possible. Today I'll be talking about observing transients near the sun with NuSTAR. As many of us know, when we go to write a proposal, when we go to plan observations, we have to check the sun constraints for all of our observatories. And we know that, if an object lies within about 40 degrees of the sun, then usually we can't go look at it at that time. And so here I've put together a plot that tries to illustrate the kind of magnitude of that inaccessibility on the sky. And so what I've plotted here are maxi transients in blue dots and red X's. And you can see they're scattered all over the sky, but they sort of are clustered around this area, which is the galactic disk, of course. And then on top of that, I've plotted the path of the sun throughout 1 year as this orange line. And this orange patch here shows that 40-degree circle of the sky that's inaccessible. Particularly, I put it when the sun is closest to the galactic center, because that's when it's covering up kind of the most active region of the sky for X-ray binaries. And those red X's that I'm showing are objects in the Maxi catalog that were inaccessible due to sun constraints, within this 40-degree patch, basically, at the time of their discovery. And so we can see that it's a not insignificant number of objects. So due to the risk of damage or being blinded by high background, many X-ray observatories can't access that orange patch that I showed, that region near the sun. This applies to NICER, Swift, XRT, Chandra, and XMM. And while NuSTAR does have this sun constraint, technically if you go to your proposal tools and you check the visibility, it might tell you, a source is within 40 degrees, that it's constrained by the sun. But it is actually technically capable of looking near the sun, because its imaging capabilities mean that, of course, we can separate source from background. And its multi-layer insulation thermal blanket protects it from getting overheated by the sun. Whereas an instrument like Chandra, which is, or any of these other instruments really, which is made to be sensitive to the soft X-rays, it can't have that thermal blanket because it'll decrease the sensitivity, but that means that it can't look near the sun, or else it'll overheat. And so here I'm just showing plots from Brian Grefenstedt's paper in 2016, showing direct NuSTAR observations of the sun itself. So I think that really dramatically illustrates this capability of NuSTAR. But looking near the sun does come with some challenges. So generally speaking, when NuSTAR observes a source, typically the star tracker on the optics module on the right here is the one that's used to reconstruct images. This is known as CHU4. CHU stands for camera head unit. While there are 3 other star trackers on the spacecraft bus that are used to control the spacecraft attitude. And images reconstructed with CHU4 are known as mode 1 data. So that's the scientific data that most of us are probably used to dealing with. But when CHU4 is blinded by the sun, we have to rely on CHUs 1, 2, and 3 to do the astrometry and do the image reconstruction for us. And this data is known as mode 6 data. Without CHU4, our image reconstruction is a little more difficult, and that's due to thermal flexing of the spacecraft bus. That's not perfectly well understood. There's a lot of moving parts, essentially. And that when we reconstruct an image using CHUs 1, 2, and 3, it introduces much larger astrometric errors, plus or minus 2 arc minutes or so, compared to 8 arc seconds with CHU4. And in addition to this, just overall uncertainty as to the pointing of the spacecraft, the resulting images can also exhibit multiple centroids. So here I'm showing an example from the NuSTAR Observatory Guide. And this is an example of a single source, not an extended source, not a group of sources or anything like that, that due to poor, or I shouldn't say poor, but difficult image reconstruction with the star trackers on the spacecraft bus, it's kind of moving around the detector like that. And so because of this, mode 6 data requires a little extra care when we're handling it. And so in order to construct scientific data products, we, in some cases, depending on how bad this kind of like source splitting is, we may have to split the observation itself up into different sort of sub-observations corresponding to the combinations of of spacecraft or of star trackers that were in use at that time. So here I'm showing an example of that from a source that I'll talk a little bit more about in just a minute. Where here on the left, I'm just showing the image using all the mode 6 data. So just every mode 6 photon. And then when I run this routine NuSplit-SC, which just comes with NuSTAR-S, then it splits it up into these 6 different shoe combinations, essentially. And you can see that they're a little bit closer to that like single centroid that we're used to seeing in mode 1 data. There's still a little bit of that splitting. But the thing that I also want to point out is this, I don't know if you can see the green region, probably not because it's really tiny, but the green region is basically, it's at the same position in all of these images, but the source itself is kind of moving around on the detector because again, our reconstruction of exactly where NuSTAR is pointing is not perfect. And so our image reconstruction and our localization is not as good with mode 6, but spectral and timing data is still intact, even though the imaging is poor. And so we can still do really great science with mode 6, which I want to talk about now. So to kind of demonstrate what we can do with mode 6 data and kind of like show that there's really few limitations, I think, I want to talk about Maxi J 1848-015. This was an unknown transient that popped off near the sun at the end of 2020. And actually it went into outburst right when the sun was at its closest to the galactic center. So you might notice that this plot doesn't look very different, right? This patch hasn't changed. That's because it actually went into outburst at like the almost exact moment when the sun was nearest the galactic center. So kind of like the worst timing, but also the best timing for this talk, I guess. So here I'm showing the position of that transient in cyan, and again, just showing the source there. And so this, the paper, or the results I'm going to talk about are summarized in the paper in AppJ that was accepted this year, and it's also, you can find it on arXiv. And so I just want to give a quick overview of the source and what we were able to do despite being so close to the sun. So here is the Maxi light curve and the hardness ratio over time, and you can see around the end of December again, excuse me, around December 20th of 2020, it went into outburst, and it has a notably short outburst of only a few days. And so, but I proposed for NuSTAR observations despite the sun constraint, and we got a quick NuSTAR observation here, shown as this blue bar, right as it's starting to go back down from this short outburst. So really perfect timing. And then again later, as after it had settled down a little bit, we got another observation just to see how it had evolved. So I'll be talking about those NuSTAR observations in particular. So what were the knowns and unknowns about this source? So at first, of course, Maxi has a big localization error. And so it was possible that this is actually a previously known source that's just, that's coincident in that error. And so the first thing we wanted to do is to localize the source. And so with that first NuSTAR observation, we were able to localize it to a region of about 90 arc seconds. And this made it look like, okay, this is probably a new source. There was a source, a catalog source that was close to this region and slightly overlapping. But it seemed that based on this first NuSTAR observation that it was actually a new source. This localization then laid the groundwork for further observations a couple months later. So, now other observatories don't need to tile, they know basically where to look. And so by the end of February, Swift, Chandra, NICER, and Meerkat had all observed the source and really narrowed down the localization. And so by March, we knew that it really was a previously uncatalogued source. And we found that it was, we didn't find. These precise localizations determined that it was coincident with the galactic cluster Glimpse CO1, which is maybe like between a globular cluster and some other kind of like, in terms of categorization, maybe not quite a globular cluster, but looks like a globular cluster. And so from that, we got a distance, which was 3.3 kiloparsecs. Okay, so we knew the distance, we knew where it was, but we still didn't know the nature of the accretor itself. Was it a black hole or a neutron star? And what's up with this like really short outburst? And so these are the light curves from those two NuSTAR observations. And you can see that the light curves are reconstructed quite well. Here I'm showing in different colors the light curve, the parts of the light curves that were reconstructed with different Chu combinations, which I'm showing in, which are labeled here. And you can see that, at different points in the orbits, we're using different Chu combinations because again, we're using those star trackers on the spacecraft bus. So as we're kind of moving around the Earth, different star trackers are going to be blocked, and different star trackers can see. And you can see there's some variability in the source. I was hesitant to do too much kind of speculation about the variability because, as I showed, the source can be moving around the detector a lot because it's in this sun-constrained mode, and so I think it probably takes a lot of really careful thinking and careful analysis to separate, variability due to the source moving close to the chip gaps and things like that versus real inherent variability. But we got a nice spectrum out of each of these observations. And so here I'm showing the blue spectrum is in the high state, and this yellow-orange spectrum is in the low state. And we can see immediately just by eye that the blue state, the high state, is really has dominated by thermal emission, and the low state is a harder state with a just parallel emission. And you can probably see here with the different model components that there's more to it than just like a disk black body or a parallel, and I'll talk about that in a second. And so one of the things that popped out to us after modeling just the continuum was these broad iron lines, and of course, as folks here know, this is often a sign of relativistic disk reflection that's broadening otherwise narrow lines. And so we did model the iron emission as well as the higher energy emission with relativistic disk reflection, but we also found that it required a narrow line on top of it, and a narrow line that actually shifted between the soft high state and the hard low state. And so in more detail, in the soft state, we see this hot disk, 1.4 keV, and a soft power law, and we see black body reflection. So we found that in order to model the reflection, we needed to use RelZel-NS, which is designed to model reflection of like a neutron star black body, like a surface of a neutron star or something like that. But it's also been used to model returning radiation from the disk itself. And so that's kind of how we interpret that spectral component. And then in the hard state, we see, again, a hard power law, and this time the reflection is modeled by power law reflection using just RelZel or RelZel, like with the light when it goes to RelZel LP. And so, we see very clearly evolving disk properties. And kind of an interesting note is that in the soft state, it only had a luminosity of 10 to the 36 ergs per second, if we believe that distance that I mentioned before, which corresponds to an Eddington fraction of only 0.5% for a typical stellar mass black hole. And so that's kind of one of the intriguing aspects of this this binary is it's got this hot disk that's clearly like coming into close to the black hole or close to the compact object, and then there's really low Eddington fraction. So what's going on there? So initially, I tried to just model each of these spectra individually, particularly because their spectra look so different. I thought, okay, well, they're two very different spectra, two different models, so I'm going to model them individually. And what I found, not too surprisingly, was that the posteriors were not particularly well behaved. So here I'm just showing corner plots of the parameters, and the actual details of which parameters are which doesn't really matter here. What I want to show is just that these posteriors are kind of all over the place, and there's a lot of very, very obvious degeneracies between parameters. And we really needed to do a joint fit in order to measure disk parameters like spin, inclination, and inner disk radius. So that's what I did. I basically I fit both spectra at the same time, and I tied together parameters that I thought were pretty unlikely to change on the scale of a week, which is the time that took place between this soft state observation and the hard state observation. Things like the compact object spin is not going to change on that time scale. Inclination is unlikely to change dramatically on that time scale. But of course, the inner disk radius can change for sure on that time scale, and things like the obscuration. And so by doing this fit, carefully thinking about which parameters are going to move and which are not, we really were able to pin down those degeneracies and get good constraints on things like the spin, inclination, and inner disk radius, which I'm showing here. So the important thing to note, I think, is that the spin is very high, and we get a very precise measurement of it. And so just looking at these posteriors, you can see they're much better behaved and definitely fewer degeneracies. A few here and there, of course, between things like the spin and the inner disk radius, but that's unavoidable. And so the takeaways from the spectral analysis, in brief, the spin is almost maximal. We took this as evidence that the source is a black hole rather than a neutron star accretor, because even the most rapidly spinning neutron stars that we know are unlikely to approach spin parameters of greater than 0.6 or so. And even in the individual fits we did, even if you're skeptical of the joint fitting, even in the individual fits, the models prefer spins above 0.7, 0.8. We find moderate inclination of the inner disk. The reason this is important is because we saw that low apparent luminosity. One easy way to deal with that would be to say, oh, well, it's a high inclination. So if we just account for that, then the actual luminosity is higher. But the disk that we found, or the inclination that we found, is only a little less than 30 degrees. Of course, we know that the inner disk inclination might be different than the inclination of the system itself, but absent evidence on the sort of system inclination, we don't see evidence for high inclination. We do see evidence for mild disk truncation with the disk moving from 3 RG in the soft state to 8 RG in the hard state. And interestingly, we see these shifting narrow lines moving from 6.8 kV to 6.3 kV or so. And this might indicate changing ionization. That's probably the most likely explanation, is we're just seeing changing ionization in the disk. But I think one of the things that kind of led us to do a little bit more speculating was that the line in the hard state is not 6.4 kV, but 6.3 kV, plus or minus 0.1, but with a sort of significance of about 2 sigma, it is redshifted, quote unquote. And so again, very speculative, but we think we suggest in the paper that maybe rather than just changing ionization, we're seeing some kind of outflow, and the sort of shifting that we're seeing, where we see the high energy line first and then the lower energy line later, is actually just the difference in distance between the blue shifted and red shifted regions of this outflow. And so here I'll just go through the summary really quick. I think each X-ray transient represents an opportunity to study unique behavior. I think everyone here would probably agree with that. And rapid follow-up is often key to our understanding, seeing how these things evolve. But much of the sky is off limits because of the sun, but not for NuSTAR. And I tried to show that Maxi J1848-015 represents an example of like the very cool science that can still be done using rapid follow-up near the sun. It had a very short outburst, that we would not have thought this outburst if not for NuSTAR's ability to do this. And we managed to classify the source, localize it, all of this stuff that sets the groundwork for future investigations, which will hopefully be able to more solidly answer some of the questions we laid out. And in terms of future work, we have an accepted TOO program to follow up more Maxi sources near the sun, and we actually just triggered the first of these, and it's being observed right now by NuSTAR. Thanks.
Yeah, thank you. I think we have time for 1 or 2 questions. Since the talk canceled in the morning, so we will try to make a little bit flexible. Yeah. Any questions? Go ahead.
Hello. So I just have a question, a curiosity. So you say that even if the position reconstruction is not completely correct, so you have these multiple spots in the image, the spectral and timing extraction is correct, but you still split the image for the different units as you showed. So is it really relevant, or can you just use the picture on the left to draw the extraction region and obtain correct products?
Yeah, so I think in some cases, you probably can just draw a big circle. I was hesitant to do that because I think there's changing, changing response across the detector. Different pixels have different gains, things like that. So the pixels are not perfectly uniform. And so I think it's the safest thing to do is to really, go in and take a source region for each of these and then add up the spectra. That's what I did. But I think, I think it's going to change on a case-by-case basis.
Any other questions? Okay, if not, let's thank the speaker again. At the same time, let's transit to the next speaker.
Thank you.
So next speaker is Enric Bozzo. He will talk about 3 symbiotic X-ray batteries.
Okay, hello everyone. First of all, let me thank the organizer for the opportunity to speak here today. So this talk will be focused on a special class of sources that are called some symbiotic X-ray binaries. Several of them are also transient, so say somehow connected to the previous talk. In particular, we will focus on 3 of them that you can see listed here in the title. So first of all, what is a symbiotic X-ray binary? So as I said, these are rather special sources, quite rare. So we have in these systems a neutron star, which is accreting from the wind of a low mass giant star, an M giant star. And it's a puzzling system because on one side we have evidence, as I will show, of a young neutron star, so possibly strongly magnetized, and on the other end you have this giga-year-old companion, an evolved M star. In X-rays, they are characterized by a luminosity that is let's say around 10 to 34 to 10 to 36 erg per second, so a relatively faint system, 10 to 36 at the very most. They show flaring behavior, so not only outbursts, but they are flaring up and down all the time. This is typical of wind-fed systems, so where you have a neutron star accreting from the stellar wind. They have peculiarly long spin and orbital periods, so a spin period can reach several thousand seconds, while orbital period can be as long as several years. So these are very wide systems. Also, they show strong and high pulse fractions, so can reach 80% or so. And also from the spectral point of view, they really resembled other systems with X-ray pulsar. For example, the more common high-mass X-ray binaries with supergiant OB companion. As I said, these are peculiar systems. So there are literature studies about the evolutions of this object. And you can see here an example. So how you can reach a state where you have possibly a strongly magnetized neutron star, quite young, coupled with a whole system. But there are a lot of details in these studies that are still poorly known because the evolution is very long, giga years, and then any uncertainty on, especially on the accretion ejection process on the neutron star, but also the magnetic field decay, they play a big role. So we don't know yet exactly how this object can form in all details. As I said, so it seems to be. Okay, as I said, these are rare systems. The first of them were discovered in the 70s. So you see in this table summarized all the systems we know so far in so many years. We end up only with 12 objects so far listed on the left. Sometimes, as I said, they can really be confused with other X-ray pulsar system. So often we end up scratching away objects from this list rather than adding new ones. For example, the one you can see removed in red, it's from 2020. This system was reclassified as a high mass X-ray binary, so it's no longer a symbiotic binary. All the rest so far are confirmed. You can see the second column, the pulse period is not known for all of them, but it's ranging from under 13 seconds up to almost 7,000 seconds. So these are very slow rotator. The orbital periods are much more uncertain. So there are multiple detections that are not yet confirmed for several systems. The record we got so far is for U1700 that was confirmed to have an orbital period of 12 years in 2020. So very recently. For all the others, it's really poorly known. The luminosity we spoke already, and well, you also have the distances on the right. So why these objects are particularly interesting? Well, first of all, these are rare objects, so they are interesting by definition, but there are two aspects that are really characteristic of this system. The first one is that as I said, it's very strange to have on one side a strongly magnetized neutron star, as the spectral and pulse fraction suggest, coupled with a giga-years-old companion. So how this can happen? Well, let's say the basic idea is that most likely what is happening in this system is that the neutron star was not there since the beginning. So the original progenitor was actually the progenitor of a white dwarf who has been accreting the stellar wind of the red giant for giga-years, and then only later on collapsed into a neutron star, giving rise to this strong magnetic field. Now, the process that is called the accretion-induced collapse of a white dwarf is still poorly known today. So in principle, if you measure magnetic field of 10 to 12 Gauss or so in these systems, this is a step forward in our understanding of this process, and we can confirm that this accretion-induced collapse can produce magnetic field as strong as 10 to 12 Gauss. That is a highly debated topic in the literature. And the second point is about stellar wind. So especially in the last decade, it was recognized that wind-fed systems with neutron stars are particularly interesting not only as laboratory of accretion physics, but also as laboratories of stellar winds. The idea indeed is that you have the neutron star moving around the companion. So you have actually a probe in situ of the stellar wind. So you can use the X-ray observation to study the structures and the evolution of the stellar wind. Concerning the second point, just let me mention for completeness that there is now a wide group of people comprising stellar wind experts with colleagues from the X-ray binaries perspective. And what we are trying to do in this is to test how much can we learn about stellar physics, stellar wind physics, using X-ray binaries. So what you see here, for example, is an attempt that is being improved as we speak. For example, what we have tried to do is to get what you see on the left, some hydrodynamic models of stellar winds that come from people studying isolated stars, especially supergiants. And then you plug the neutron star, you try to compute the feedback because the neutron star is disrupting the wind and so on. You produce a synthetic light curve to be compared with X-ray observations of wind-fed binaries. And then you try to do some reverse engineering to see how much you can learn about the physics of the stellar wind. So this effort is ongoing. So far, it has been focused on supergiant stars, so high mass X-ray binaries with supergiant stars. But we are also trying to refocus on the field of symbiotic X-ray binaries to study what we called the dust-driven winds of a red giant star rather than line-driven winds from supergiant stars. So going to the first object of the list, this is IGR J17329. This was the most recent discovered symbiotic X-ray binaries. It was discovered in 2017 by Integral. This is why it's called IGR. Immediately after the discovery, we followed up the source with XMM Newton and NuSTAR, as you can see in the bottom plot on the left. So you see the light curve is heavily peaked with the spin period that is almost 7,000 seconds. And very interesting, the NuSTAR spectrum showed clearly the presence of a cyclotron line. You see this this bump in the residual around around 20 kV or so. So this gave us the first indication ever that indeed symbiotic X-ray binaries can host strongly magnetized neutron star, because a cyclotron line at that energy corresponds to a magnetic field of several times 10 to 12 Gauss. So following this discovery, and of course this very interesting source, we followed up the source for several months after the initial outburst detected by Integral. And here on the left, you see the results that we just published this year. This is a 9 months monitoring program with XRT. Each point is an XRT observation with Swift. And it's taken every day. So every point is separated by the previous and the next one more or less by 1 day. What you see from this plot is that, first of all, the source never turned off. So it was discovered, it turned on, and then it stayed variable but persistent, as it is expected for a symbiotic X-ray binary. But in the middle period, what you see very interesting are these flares here, up and down, that looks quasi-periodic. And what is very interesting is that if you compute the XRT spectrum during the flares or in between the flare when the source gets faint, you see that there is a strong spectral variability with this huge iron line coming out. So if you are expert about X-ray eclipses, this spectrum here in black, when the source is faint, is exactly what you expect during obscuration. So when the X-ray source is obscured. So what we concluded is that what we observed during this period, most likely, is that the neutron star was probably interacting with some big structure coming from the giant wind, something that is similar to what has been observed also in Betelgeuse. That is a different kind of star, but it has a very nice artist representation. So I use this one. You can imagine that when the neutron star is crossing one of these very big structures, it can produce flares, but it can also be obscured. So this is, of course, a possibility. But what this is telling us is that indeed the idea of using this system as probe of the stellar wind is working, because monitoring them, you can actually detect and study this structure in the stellar wind that otherwise are very difficult to be detected. So summarizing the status of this source, we call this a milestone symbiotic X-ray binary. First of all, because again, it showed for the first time the presence of a strong magnetized neutron star, 10 to 12 Gauss or so, meaning that indeed, as of today, we can say that the accretion-induced collapse of a white dwarf should be able to form such strong magnetic fields. The interesting point is also that this source was never observed in X-rays before. So before 2017, from that position, we never recorded X-rays, meaning that we called this one the birth of a symbiotic X-ray binaries. Now, what does it mean? It's really difficult to tell, because in principle, these systems are very old. The red giant was already there with the wind and so on. So we cannot really conclude what is the reason for which this system never shine in X-rays before 2017. Could be that it just achieved the status where the stellar wind is strong enough to power the accretion on the neutron star. We actually don't know. That's still an open point. But of course, we can say that definitely after the discovery, this source stayed more or less constant but variable, as expected for a wind-fed symbiotic X-ray binary. And indeed, these obscuration events are very interesting. So we want to study further the source, eventually to reconfirm also the cyclotron line, but also to continue detection of these events that can tell us so much about dust-driven winds from M giant. So let me go to the second system, for U1700. This is an historical, I would say, symbiotic X-ray binary. So it was known since the 70s, so discovered by the Uru satellite. Is known to be highly variable, produces also outbursts that are often detected by MAXI and Swift with, let's say, a very high dynamic range in X-ray luminosity, about a factor of 200. And it has this record period of 12 years that was confirmed in 2019. And you can see here basically a summary of the existing observations so far. So it was quite well observed below 10 kV, but above above 10 kV, I think there is only one RXT observation, and that's more or less it. So despite its very interesting source, it was poorly observed in X-rays so far. So what we found interesting is that there was a NuSTAR observation performed a couple of years ago. You can see here the spectrum of the source. The light curve is variable as expected for a wind-fed system. But what is more interesting is that if you use a cutoff power law to describe the spectrum, that is the typical model used for this system, you can see in NuSTAR quite evident residual around 16 kV, and also some evidence of residuals around 31 kV. So clearly, this quickly reminds about the presence of a possible cyclotron line. Indeed, if you fit the spectrum in a detailed way, you do see that these residuals completely disappear if you add a cyclotron line. So the fundamental line has 16 kV, and the first harmonic at double this energy. This is, to be honest, not the only way to get rid of the residuals. Another possibility is to add a high temperature black body about 1.5 kV, and then the cutoff power law. Now, of course, the cyclotron line interpretation is more interesting because it will tell us that this is the second symbiotic X-ray binary showing evidence for a strong magnetic field. On the other hand, yeah, the black body fit is still possible, is still an explanation. But what we found strange is that analyzing the data during the outburst, several outbursts observed by Swift, you can see the combined simultaneous XRT and BAT spectrum. Here, there is no evidence of such black body. The full spectrum is fit by simply using a cutoff power law. Unfortunately, you cannot see the cyclotron line because there is a gap in the data exactly where the cyclotron line should be, but is most likely telling you that probably the cyclotron line interpretation is the correct one. So definitely, since this is the second symbiotic X-ray binary with this feature, we aim at obtaining further observation to confirm this detection. Third and last system, and then I conclude. Unfortunately, with this other historical symbiotic X-ray binary, we were not so lucky. So this is called Sco X-1. It was again discovered in the 70s, but it was even less observed than the other one. So the summary of, let's say, the available observations is more or less here. You go from observation in the early 80s up to an observation that of XMM that was published in 2007, where you can see the source was still relatively bright and highly variable. Unfortunately, when we got to the source with the next campaign, that was a Chandra plus NuSTAR observation in 2020, you see the source was fainting down a lot. So it moved from 10 to minus 10 in flux in the 80s down to 10 to minus 13 in flux in 2020. So this is, of course, here it's impossible to look for cyclotron lines given the statistics, but the observation was not in vain. It is still very interesting to see that this source underwent a secularly decrease in flux. It's not the first symbiotic X-ray binary. We know at least another one that made the same evolution. And this is interesting from the stellar point of view, because in principle, you expect that the stellar wind should always be there, as well as accretion. So the reason for this secularly fainting is not at all understood. We are investigating this with our stellar colleagues. We have no explanation so far, but it's clearly something that is interesting and to be explored in the future. So with this, I conclude, and thank you very much.
So there's a comment in the chat window. Marilla, would you like me to read it, or you can start me?
If you want, I can read it, if you can hear me.
Yes, we can.
So I was just saying that, first of all, a comment about the name, because there is a very large class of symbiotic X-ray binaries that we know as such, and grows with the white dwarf, also making X-rays of quiescence. So maybe you should just call them neutron star X-ray binaries to avoid confusion. But second of all, I don't know about the detailed wind studies you mentioned, but I know that there were some detailed studies for white dwarf symbiotic X-ray binaries. And it seems that often this can be built either because of the wind or because the red giant is completely puffed up and not a regular red giant. And so there is an accretion disk, even if there is no Roche lobe filling. So I wonder if that may be the case also in the case of neutron star X-ray binaries.
Yeah, that's a very interesting question. So indeed, when you have a wind-fed system, sometimes you can also form a disk. Usually this is difficult because the angular momentum is very low compared to the Roche lobe overflow. So to form a disk in wind-fed system, what you need is to slow down the wind in order to increase somehow this angular momentum. And this can happen especially if the neutron star is very bright. So for example, when you go above 10 to 36 erg per second, you can photoionize the wind, you can stop the acceleration of the wind, and we have cases, especially in supergiant high-mass X-ray binaries, where we believe that at least the temporary disks are forming. However, the observational evidence of this is quite poor because there was so far no detection of broad iron lines, for example, that can testify the direct presence of a disk. So we don't have an answer, but in the case of symbiotic X-ray binaries, this will be even more difficult because the luminosity is low, so you don't expect a strong disruption of the wind. On the other hand, there is still a lot of work to be done because in this case, in the symbiotic X-ray binaries, the wind is dust-driven, is non-line-driven, so the way in which you slow down the wind is completely different, and I believe as of today, we don't really have calculations about the feedback of the neutron star onto dust-driven winds. All the effort so far was on line-driven winds from OB supergiants. So that's still a point to be explored. But with such low luminosity, I would say that's quite difficult to get a wind. Sorry, to get an accretion disk.
Yeah, the ones I was mentioning are, the same conditions, relatively low luminosity, even lower than the neutron star X-ray binaries. And there are mainly observational evidences. I don't think the models are very detailed and more phenomenological, but the claim is that you can form a disk with these dust-driven winds. I don't know any more than that.
Okay.
But I can point you to the papers if you want.
Yeah, with pleasure. Thank you.
So there's a question in the room chat, but at the same time, next speaker can translate because it's already 20 minutes. So the question is, have you observed spin period derivative in any of these sources?
Sorry, can you?
Have you observed spin period derivative in any of these sources? P dot.
I'm thinking. Yeah, I believe there are measurements of. So I think, as far as I remember, I hope I remember correctly, the only measurements we had was for this system that was recently reclassified as an high-mass X-ray binary. So I believe for the other systems, no, we don't have measurements of the spin up, spin down. I have to check, but at the top of my mind, I don't have a reference paper to suggest. So the other system was reclassified, so it moved out of the table. For all the others, I'm not aware of any measurement. Also because the spin period is very long, so it's difficult to check changes. Yeah.
Thank you. So any other discussion can ask in the chat Slack window because it's an interesting source. So we'd like to move on to the next speaker. So next speaker is Romana Mikusincova, who will talk about the Coronal properties of weakly magnetized neutron star in low-mass X-ray binaries.
Hello, everyone. Thank you for coming. I also want to thank the organizers for giving me the opportunity to speak at this conference and introduce my work to you. My name is Romana Mikusincova. I'm a PhD student of Georgia Math at the University of Roma Tre. And today I will talk about coronal properties of weakly magnetized neutron stars in low mass X-ray binaries. So I will a little bit elaborate on Francesco Orsini's talk from yesterday, who spoke about studying the coronal properties with polarimetry using NuSTAR and also IXPE. IXPE truly did open a new window of opportunities when it was launched last year in December. And it has among the main targets for the first year of observations with IXPE these three sources that we see here. So all of them are neutron stars in low mass X-ray binaries. And so it's GS 1826, then Cygnus X2 and GX 9+1. And the thing is that from IXPE alone, unfortunately, we're not getting super good fits. So it's always better to have multiple different observations performed with multiple missions. Also, if we want to make predictions about the polarimetric properties of the studied sources, we need to have some sort of good constraints on the parameters that we study in these sources. So it's better to use spectroscopic observations and constrain some of the parameters from that when we want to later on, when we want to model the polarization with IXPE. So that's why, that's basically the motivation behind this work. So to guide the simulations, we will need to obtain some good information from the spectral data, which we did using some observations of these sources with NuSTAR. So in this work, we basically analyzed an observation from 2014 of GS, and then observations of these two sources from 2019. What we sort of considered in our work is that for both the sources, we compared two basic models where we have a geometry of a shell corona, which we can see on the picture on the left here. So we have basically the corona is covering the neutron star and we see the disk directly, while in the other scenario, we have a slab corona which covers the accretion disk and the neutron star is observed directly. So we will use some models to account for the thermal radiation based on the model used, and then some Comptonized model or component to account for the photons scattered on the corona. Now, in the real case, of course, the photons from both the disk and the neutron star will be sort of scattered on the corona, and we could use two Comptonized components in our analysis, but that would be way too difficult to fit. So we will just try to make this as simple as possible. So for these two sources, for GS 1826 and for GX 9+1, we just used a very simple model with either, well, with black body, depending on whether we have a shell or a slab corona, and then we used a Comptonized component. However, for the case of Cygnus X2, that is not as easy because we have some reflection component, as we can see here on the bottom panel. So we also have to account for this, and we did in this study using the Relxil model. So these are the results of the first source. So GS, you can see for both, basically for both the cases with the slab and the shell corona, we got some reasonable statistics. And you can see here, I'm reporting the best fit parameters. For both of these cases, I mean, we had two intervals that we studied. That's why I mean, those parameters were not tied together. That's why I'm showing two numbers for each of the parameters here with for the temperatures. Not sure if this is visible. Okay, so for the temperatures and for the power law, while the coronal temperature was tied in between these parameters, so we only have one value here. you can see that the fit with the Western model is a bit less physical, because we have basically we obtain that the disk temperature is way higher than the neutron star temperature, which we expect it to be the other way around. And also the neutron star temperature is way low. This should be around 1 or 1.5 keV. And you can see that it's very low. Basically, it's like around 0.5 keV. So for this reason, the shell corona seems to be, the model with the shell corona seems to be more favorable. We also tried switching these two temperatures. So we basically put this value as the disk temperature, while this value was used for the neutron star temperature. So we tried switching them if we get a better fit, but unfortunately this did not happen. The fit got even worse, in fact. So this really does speak in favor of the so-called Eastern model or the shell corona. Moving on to the next source, which was GX9+1. So both the models seem to be quite similar. They are very physical, so this is really good. However, for the Western model, so the slab corona around the disk, the temperature is a little too low. So we only got around 0.3 keV for the disk temperature, which is here. So this again speaks a bit more in favor of the Eastern model. Okay. Now, moving on to the last source, which was Cygnus X2, I said that we used not just two different geometries for corona, but we also used two different reflection models, which was RelXil and RelXil-CP. So we tested also those two against each other. I'm just showing very preliminary results here because we've been kind of struggling with those fits, and we get in really good values here, and it is definitely a work in progress. So you can see in the table here that basically, I mean, one of the issues with this model and also with the next one with the RelXil-CP is that we are getting again, we had two intervals that we studied together, and they did not have the parameters of them were not tied. And then you can see that some of the values really are totally discrepant, so they don't really, match together, which is kind of an issue that we want to fix later on. We want to work this a bit further. For example, in the case of the disk temperature, you can see that we got 1.9 keV for the first interval, while for the second one, the value was almost 1 keV higher. So this, points to the fact that something's not really working well in here in this model. The same basically goes also for the other scenario of the different corona geometry. Same goes also for the, basically all the other parameters. The neutron star temperature here is also quite weird, and the gamma factor. I mean, we really did not get a good value for the Paolo. So this really points to the fact that something might not really be playing out in our favor, and we might want to try a different model to fit this data with. I'm going to get to that in my next slide. So I'm just also showing really quickly the RelXil-CP fit results here, but you can see that also the fit statistic and the parameters, they are not really satisfactory. So we will be playing around with that a little bit more. So this basically brings me to my last slide, which is the conclusions. We have seen from this study that we have performed that for the source GS 1826, the Eastern model was more favorable So that's the one with the shell corona covering the neutron star. So that one was more favorable, while the slab corona gave us a bit unphysical results. For GX9+1, both the models were similar. They both were giving us quite good results and satisfactory statistics. However, for the slab corona, the disk temperature that we obtained from the best fit was a little bit too low. I remember that it follows from some of the previous observations that they are more in favor of the Eastern model, so this is good so far. The Cygnus X2 is still a work in progress, so we will be playing around with that a little bit more. There is this new RelxSeal model specifically designed to fit neutron star objects, which was also presented by Renel alum on Monday in her talk and got published. I think it got publicly available about a week ago. So we are planning on, in the future, we are planning on using this specific model on Cygnus X2. On the bottom panel, you can see basically what happens after the spectral analysis takes place and we get some of the parameters constrained. I mentioned at the beginning of my talk that we need this in order to somehow satisfactorily model the polarimetric properties of the sources and then to be able to fit them well once the data arrives. So this here is a plot by Andrea Agnarini from his paper that got accepted quite recently. This is a generic simulation with the corona temperature of 3 keV and the neutron star temperature 1.5 keV, and we see the polarization degree on the bottom panel and on the top panel, and then polarization angle on the bottom panel. We see that for both the shell and slab corona, they are very well distinguishable from each other. And what we can see here basically, so for the shell corona, on higher energies, the source gets a bit depolarized due to the spherical symmetry of the source, while the disk is more dominant on lower energies. That's why we have a slightly higher, I'm not sure if this is working. That's why we have a slightly higher polarization in here on this about 2 to 3 keV energy band. And then for the Western model, the Compton scattered photons from the accretion disk, they are more dominant on the higher energies. So that's why we also see that the polarization degree is rising. The first, not the first two, but GS and Cygnus X2, they have already been observed with XP earlier this year. I think it was around March and April. Or March, April, May this year. The data are currently being analyzed and are soon to be published. And then GX9+1 is planned for an observation in October this year. So I'm very excited about seeing the data from that one as well. And basically, we will be continuing with this analysis and with then simultaneous observations with IXPE and NuSTAR. I think there's also an observation with NuSTAR planned for some of the sources. So this is it from me, and I thank you for your attention.
Any questions?
Sorry, can I ask a question?
Yes, go ahead.
Yeah, so hello, thank you very much. It's a very neat talk. I just want to ask you, are you actually looking at the IXPE data?
At the XP data?
IXPE data, so the polarization data.
So in this analysis, no, this was just NuSTAR data, but I mean, they are being currently analyzed.
So at the beginning, when you comment, you're saying that only IXP data, you cannot get a really good fit. What does that mean?
I mean, of course, it's better to have, you know, complementary observations, not just with XP, but also some, you know, spectroscopic measurement to have way better constraints on some of the parameters, because, you know, you could see that it's quite difficult to constrain the temperatures and some other parameters of the source.
Yeah, of course, but it doesn't mean you don't get a good fit, right?
No, of course not. I mean,
okay,
you can rely on the fit, but just to some extent, and, you know, to make it even more, you know, reliable to, you know, just basically just to get, just to make it more reliable for you, and to get way better. So this is sort of like, maybe,
yeah, of course,
being a bit of a perfectionist in here. So that's why you want to have both, but of course you can rely on XP measurements.
And I just want to ask, are your NuSTAR observations simultaneous to your IXPE observations?
Okay, I have to say I currently don't really remember, because I know that, I mean, some of them, yes, but I think there was one observation that was not really simultaneous, that I think the NuSTAR was a little bit earlier than XP, but I'm not really sure. Maybe someone else can comment on that.
Yeah, so I just want to say that, first of all, this was already shown by previous talks, like Jiang already talked about black hole X-ray binary, which is a bit different. And then also shows some AGN corona too, and it can actually change corona geometry. And it depends on the flux and all of these things. And it's just me. I personally think it might be good to have simultaneous data. And because you were talking about Sino X2, I don't really know the other twos. So I have AO observation on Sino X2, and it's simultaneous with IXPE. So when you talk about your data, so I was like, okay. But I just want to let you know that I'm very happy to collaborate with you and your group if you want to have access to the NuSTAR data. But I just like, because I don't really know which NuSTAR data you're looking at right now. But if you are very interested to the simultaneous data, NuSTAR data of this object together with IXP, I'm very happy to collaborate and also, you know, help making models for the reflection components as well. You already mentioned the reflection component is complicated and all of these stuff. That's it. Yeah. Thank you.
Of course. Thank you as well.
We still have time for more questions. So you don't know the polarization property of any of this source yet, right?
I mean, they are currently being analyzed. I can say that for Cygnus X2, there has been some substantial polarization measured, but it is the XP policy not to really reveal any specific data. I mean, any specific information before the analysis is complete and the paper is published. So I can't really comment anymore on that.
We still have 1 minute for another quick question. Okay, if no questions, let's thank her again, and we can keep discussing in person. Yeah. Okay, we will move on to next speaker. Norbert, who will talk about XM Newton and NuSTAR partnership.
Good morning, ladies and gentlemen. It's a great pleasure to speak to you. Maybe first a comment to this talk. XMM Newton and NuSTAR partnership. I wanted to go to this conference because XMM Newton and NuSTAR work close together in many aspects. In ESA, we have to submit a talk if you want to go to a conference. I submitted a standard talk. I think I changed the sentence. And then I forgot it more or less. And some weeks ago, I had a hole. I know I have to prepare it. I looked to the emails and I saw that my title was changed. it was the XMM+NuSTAR partnership. I am happy to do it. I asked the organizer and they said, okay, we would like to hear more or less about this. But it was the first time that my talk was changed before going to a conference. First, comment to XMM. XMM is Europe's large X-ray observatory. We have 6 simultaneously observing instruments, 2 reflection grating spectrometers, 3 CCD cameras, and an optical monitor, which is very similar to the optical monitor from Swift. And we have this high effective area from 0.2 to 7 keV. Now, going to this partnership, we have to go back. This is now my eyes. We have to go back to this AO11. In August 2010, AO11. Now, in August we call, but it is basically 1 year later we make the observations, and the NuSTAR start. The launch of NuSTAR is basically after this AO. And it was, for me, this was without any thinking. I was not expecting that there would be any request for an observation with NuSTAR, because simply this AO would be finished here. It might be that there were some overlaps, some slips later, but I was completely surprised that we got requests. Now, such requests for a mission in future is for an OTAC a complete killer. It's a technical killer. Who knows if the mission is launched? Who knows if there are delays? We want to see the data. Therefore, and this time, the reaction was completely different. All these targets were immediately accepted by OTAC of a mission not launched, and in future, not seen any data for it. This was the first time that something like this was happening in XMM. The second very remarkable thing is this enormous time in these requests. It is from Giorgio Matt, this long monitoring of several key AGNs, from Fiona monitoring of AGNs, then from Risaliti, this long monitoring, a complete surprise, first to get these targets in, that OTAC accepted it, and the big amount of this data. Now going to the next, given that it was 2010, in 2011 we had the next call. This call now nicely overlaps with NuSTAR, and again targets were accepted. Now there is a launch, and the targets accepted here, I think they were accepted mostly from the XMM side, but the people were going to Fiona, asked for disciplinary time, asked for joining. But there from Fiona, for example, there are also targets, don't know, I cannot see it. There are also targets from Fiona in addition to the NuSTAR things. Okay, what was the next step? Now the launch. Now the launch in June, but in August we open already the next AO. Now a big list of targets. I think this is a mixture, either people knowing about NuSTAR scheduling, asking XMM, other people asking for XMM, going to Fiona, asking for disciplinary time. And during this AO, there was then Harvard Center X-ray Astronomy. This was a conference shortly after the launch. And here's a rationale, long-awaited NuSTAR mission will be presented. And here is a little bit my emails from this time. I sent an email, congratulations to Fiona. Then we have 3C273. I was looking, we made, I think, a joint observation for calibration. I was looking for the detector response, and it needed then 10 years to get this calibration at the end. And, oh, sorry. And then we tried to arrange to lunch together. This was not working out in the first call, But at the end, Fiona and we could, I think, meet in the conference dinner. It was in Mykonos. And there, basically, we agreed on a joint program. For me, the important point was all other joint programs are about 300 kiloseconds, 150 kiloseconds, also a small exchange of observing time. But as you have seen in the beginning, these long monitoring programs, this would never work out in a joint program if I have only in total 300 kiloseconds. And I don't remember the details, but Fiona very quickly said, let us go to 1.5 megaseconds. And this is a fantastic number because it allows such long monitoring, joint monitoring programs. And you see then in March next year, I sent basically a first draft of the program and then our first joint program. And you see here, the time which can be given out is 1.5 megaseconds. And with this opening the possibility for this large monitoring with both missions together. Now, then in 2014, there were a long list of observations and also then here with these large observations. And this is a cumulative plot. And you see these are all joint programs, the targets, the time here. But the time is an XMM Newton time. It is not now completely all joint, but it is then connected with a joint observation. And you see it starts like this. And then when the NuSTAR joined and was also making it, oh, we go here in the range of the 3 megaseconds, 3 and over 3 megaseconds, which we perform each AO joint of the two missions. This is about half the targets from our current AO, which we are observing. And here now my question or concern is a little bit, you see, it's a very few long observations only. It is only half, we still have some, but the amount of this long joint monitoring has massively dropped. I see also a lot of large programs asking only a small amount of NuSTAR time. I am asking me, is this really that we know the sources so well, or there is in the community reluctance to ask on the other joint mission a long time? I think we must be careful here that it's not going in the wrong direction and at the end damaging the scientific results. Now, this view graph I presented for the XMM Newton mission extension in ESA, analog to the NASA. ESA is extending the mission every 2 and now every 3 years. And all this committee, the most of this committee are non-X-ray astronomers. And basically, I explain here this importance of the iron line. It is a high abundance of iron. We have this high emissivity. We have the high energy. This means if I go near to the black hole, still I see this iron line. And then most important, the iron line is quite isolated. This means if we see broad features, we can really study them. And this is even with higher resolution not possible in this soft X-ray region because these broad things overlap. And the other side is that we, with this bad resolution at the end of PN, still can get a good reasonable analysis of this line. It allows us a lot of things which in principle you could only make with higher resolution instruments. And okay, and then you see here, clearly I have to highlight XMM, but at the same time I show with NuSTAR this enormous synergy of these two missions to resolve this iron line. Now, what is our main driver? It's clearly these are the black holes. So there's a compact object where we need general relativity. If we see such a disk in the Newton region, we have seen this is M shape, special relativity, Doppler shift beaming, we get such a shape, and general relativity, we get the gravitational redshift. and we come then to this broad iron profile, which ideally is started with this iron line. Now, if we come to the Kerr solution, rotating black holes, then this line here basically can go down to such a triangle shape. And you see in the energy, a half in the energy, this is something which the resolution is less important than the isolation of the line. Now, want to make here a comparison. This broad line, I think that Sia mentioned it already, was very, very heavily discussed in the community, and this blocked it. And we needed basically from XMM papers, we needed 9 years to get these results in science, in nature. And the reason was that we had not only the spectra here, but we should know for the first time this frequency-dependent delays. This was completely unexpected. I saw the first simulation were made, I think, for Zeus, which was an idea before Athena. For this, the simulations were made. Then basically Andy Fabian started to test it with XMM data, and he could see the delays. And with this, we could get it basically in nature. Now, this, I think, is the first Nature paper with NuSTAR data. It is with this broad iron line. And here, basically, the people were taking this, this is this Resuliti program, which you saw my first selection of targets. And here you see that took the XMM data, made 2 fits, one fit basically with an absorption model, the other with a reflection spectrum with a broad iron line, and basically compared this to the NuSTAR data, and you see very clearly one fits and the other not. But the important point, this NuSTAR paper was 2013. This is 1 year after launch. This means the whole progress, which need 9 years on the other side from the legs, was basically from the spectra with the same argument made within 1 or 2 years. And this iron line is not only used for the iron line, it is not only used for AGNs, it was then expanding to a lot of other regions. These are then, sorry. These are neutron stars, NuSTAR and XMM observation. And you see here this broad iron line basically allowing to constrain the radius within 22 kilometers. We know we are much, much better today with dedicated instruments, but at this time it was a very important, very remarked constraints of the radius. Type 2 X-ray bursts, a rapid burster. And here again, the line is used with NuSTAR and XMM to get the constraint here on the disk here to get here 41.8, also 87 kilometers. And the conclusions that we have electromagnetic bursts basically. Then this detection of the neutron stars in ultraluminous X-ray binaries. This was really completely unexpected. The people were either looking to black holes with a super Eddington accretion or basically middleweight black holes, which were so considered as a step to go to supermassive black holes. And now then the first in NuSTAR data, but then very quickly 2 in joint data, one from Israel with 1,000 times the Eddington limit, then the other from Felix Fürst here, again, the XMM, sorry, this is shifted, and NuSTAR data, this ultraluminous X-ray data and neutron stars behind them, I think a very important detection. And you had seen in the first few graphs from Fiona Harris already, these several observations of ultraluminous X-ray sources, which was a really big surprise that we could explain part of them. Then lens tearing effect in a galactic black hole, also a black hole with stellar masses here. Again, XMM+NuSTAR showing this different variation of the iron line peak explained with Lansbury explanation. And this is now the status of AGN preparation mapping using the time lags to get the physical dimension in it. We can basically now disentangle the mass, the spin, and the corona and the height of the reflection. And now the latest one basically to get this light blending around the black hole and basically in some way to prove principal predictions from general relativity. And finally, I want to show this nice Pigit-Signy profile, which ideally shows how XMM and NuSTAR data come together to get such nice line profiles, which individually the missions cannot done. And this then I want to say happy birthday, NuSTAR. Thank you very much for listening, and I am happy to take questions.
Question.
So are there any plans to, I don't know, maybe even increase the joint programs in the future when maybe when the science cases for the sort of the shorter programs are sort of run out, to have even more longer coordinated observations?
Also, we have this 1.5 megaseconds, which is given out from both. It means in total 3. But we were always handling this flexible. If one had higher requests, or the OTAC approved more than was in the budget, then normally we approved it. Also, should I say, if you put such a large program in, you are down to small number statistics. Therefore, we have fluctuations. And so far, this was not necessary. And it's my impression in the last AO, I think we have not even used the time we had in the other mission. Also, as I think if there comes requests, we will discuss and we'll find a solution. But as long as the program is sufficient, we continue. I hope.
Thanks.
There's a question in the chat window. Carl, would you like directly talk over Zoom?
Yeah, I think I can. Hi, Norbert. Thank you for the presentation. I was wondering if you could expand on your concerns about the decline of long exposure XMM observations coordinated with NuSTAR. Because you mentioned that they had changed to short exposure.
Yeah, it's an observation, and the question is how much it is really science, or are people maybe artificially reluctant to ask for a lot of time in the other mission? This is my main concern. And you see, for example, we had one talk where people interpolated these gaps. And this is very nice, but it is no data at the end. And therefore, I am afraid maybe the community, maybe I should make another argument. If you have normal programs in XMM, we have a lot of seed time. This means often a program, say, ask for 5 targets, only 1 is accepted, or it's accepted in seed time. Therefore, at the end, I think some 50% of the programs get time, only a small amount of it, but they get something. In large programs, if you have a monitoring program, it's either given all or nothing. Therefore, in large programs, you have really an oversubscription from 1 to 6. Therefore, it's very unlikely to get large programs through. But maybe is a little bit my thinking, the community has the impression that this joint request is a reason for the rejection. And then they try to minimize this. They, instead of taking the full time asking, you know, from NuSTAR and both, they ask only, say, a third of the time. And then it would be very bad because this data is not taken and this interpolation is not real data at the end.
Do you see a way of restructuring how you evaluate the programs to get around this? Or being clear in the comments that go back to the proposer?
I think it's not a question of the evaluation process. I think it is maybe such a feeling in the community which is very hard to battle. Should I say, I have to write a lot of documents, these policies, procedures, these guidelines, but my experience is that very few people read it. And the community lives to a large amount from rumors. And I hope, as if there is something around in this direction, please forget it. If you want time on both, ask for it. The decision is always made in for the mission where you send it to the OTAC.
Okay, thank you. I don't see any more questions. Thank you. So our next speaker is Greg Madejski, who will talk about IXPE and NuSTAR partnership.
All right. Thank you very much for allowing me to present the recent results from XPE and how XPE plays with NuSTAR. I'm Greg Madejski from Stanford, but I'm a member of the XPE team as well. Many of you probably know that XPE is this international collaboration that I will discuss it in just one second. I need to emphasize here that there's a number of people who are members of the XPE team in an audience. Ricardo in particular is a person that I collaborate with quite closely. I suspect Andrea Marinucci might be here as well, and maybe plenty others that I'm not sure. So let me just continue here. Since nobody discussed what XPE is all about, I figured that maybe a few slides explaining the instrument itself might be in order. XPE itself, it's a satellite that is actually not all that terribly different in terms of just very sort of global structure than NuSTAR, but it's a very different purpose of the instrument itself. It was launched 6 months ago, so this is really baby by comparison to XMM, which has been, you know, already up in orbit for a number of years, or NuSTAR, which is 10 years old at this point. Is entirely dedicated to X-ray polarimetry. And I like to sort of in a pedagogical way to tell you that you probably are used to looking at the data cubes where each data bit has timing, spectral, and imaging information from where it came from on the detector surface. It turns out that there's another yet bit of information, which is basically a polarization of the X-ray itself. As I will come back to this in a little bit later, is that individual X-rays do not give you information about the polarization of the source. It's just the polarization of the one X-ray, which of course is going to be in one form or another there. Just to give you a bit of an overview, it's the 3 identical telescopes that are mounted at 120-degree intervals, and that's essential to avoid any kind of systematic effects. 2 telescopes would be a problem, okay? So you want to be in the kind of configuration that is at 120-degree intervals. The total effective area is small. It's only 100 square centimeters at 2 keV, and the bandpass goes to about 8 keV or so. And it was launched by Falcon 9, the SpaceX satellite SpaceX rocket, and went to nearly circular orbit. You might ask, why bother? Falcon 9 has a huge amount of lift capacity. It turns out that that had to be used up in order to be able to move the satellite from the orbit that would be inclined going through Kennedy Space Center all the way up to the equatorial. So it's about 0.2 of a degree inclination right now. It's at 600 kilometer circular orbit. And again, this is not a very different mission than NuSTAR. It's basically one of those pointed stair type missions. So there's no going back and forth between different missions at different places around the orbit. Many of those slides here are slides that I got from our friends, our collaborators at PISA. Ronaldo Bellanzini is basically a person who came up with an idea of the fact that you can actually measure polarization of an X-ray by looking of the electron track in the detector. So when a photon hits the detector, it actually causes the ionization, and the ionized material moves, and you can actually track it. And because of the fact that the tracking is related to the polarization of the incoming X-ray, you can actually determine the polarization of this. It's the electron track gives you basically a polarization angle. So 20 years after the invention of the instrument, finally there was actually maybe about 17 years after the invention of the instrument, there was a realization that people in the States, Marshall Space Flight Center, can develop optics, and the Italians can provide it. So it was a great collaboration. And at some point it was, at some point it was proposed, thank you. At some point it was proposed to be a SMEX mission, and in fact was selected along with the another mission for the initial study. That other mission was descoped or deselected, and XP became a reality. The instrument, as I mentioned, has 3 separate detector units, and this is a sort of a picture of the detector. The energy resolution of this instrument is relatively modest. It's only about 20% or so definitely way worse than NuSTAR. And the bandpass, of course, is rather narrow. So the important aspect of working together with NuSTAR is, first of all, to be able to measure the spectrum of the source in a much better, much more robust way. And another one is to look for the for the structure of the spectrum, and also to be able to look for spectral features here. All right. So the partnership between the two instruments basically relies on the fact that the bandpass allows the reach to higher energies, as I mentioned earlier. For the study of the non-variable sources, it almost sort of doesn't matter if you're observing the target at the same time with NuSTAR as you are with XP. However, many of the sources that have strong level of polarization are quite variable, and that requires observations that are done simultaneously. So for my own research area, blazars and radio galaxies are the objects that are so variable. Also the isotropically emitting active galactic nuclei. So I will give a few examples of the discoveries here. The policy of the instrument team is to disseminate information about XP observations and XP results as widely as possible. But the constraint is that the paper has to be at least submitted at that point. So we have the number of observations that are being analyzed. You've heard about some stuff that maybe was described a bit before the submission to the Sigma 6-1 results, but all 4 observations I'm going to reveal today are already on the archive. So if you want to dig a little bit more deeply into the results that I have, you can actually look at those. So the polarization measurement, I want to emphasize this, that requires lots of photons, because you cannot just determine the polarization of a source from just one or a few photons. You need to know if there is a uniform distribution of polarization, which means that source is not polarized, or if the polarization is preferential in any given direction, which would imply that it is. And again, as I mentioned, that this is that 4th dimension besides time, energy, and position of the event on a detector on the detector face. All right, so let me just give you at this point few highlights of XP. This is probably one of the most surprising results that came up, and many of you might have seen it. This is a paper led by Roberto Taverna, and it's been posted on the archives probably about 2 weeks ago or so. Needless to say, those anomalous X-ray pulsars have extremely high magnetic field. This is the magnetic field of on the order of 10 to the 14 Gauss, and this is not any of the information that we got from XP observation itself. This is something that has been known about the source in the past. There are 2 separate pointings of this, and this is basically 3 different detectors just to see, so you can actually see how well the imaging of the instrument works. So the very surprising result is that there were 2 separate components in terms of spectrum and polarization. That has been known in the past, that the soft X-ray emission is probably some kind of a quasi-thermal emission in magnetars in general. And the harder emission beyond few keV, it's a power law. And it turns out that the angles of the source is polarized, but it's polarized in such a way that the angle of polarization below 4 keV is in a different direction than it is above 4 keV. Let me just tell you that this plot here is sort of illustrates the way we are actually showing the polarization level. Is the angle is in an azimuthal angle, and the direction, the distance from the center of this sort of semicircle is the level of polarization. And again, you can see that between 3 and 4 keV, the polarization angle is in one direction, and above about 5 keV, it's in a different direction. So that basically implies that the emission from the subject can be explained well by a model that is known as the resonant Compton scattering model. I'm not an expert on magnetar, so all I want to do is to highlight the exciting results here. But apparently the best way to think about the emission from magnetars is that the soft X-ray thermal emission from the surface of the magnetar itself is scattered by the material that is actually farther away from the star. So again, it depends on geometry of the system and direction of the motion of the star with respect to the spin axis. So again, I probably am not the right person to elaborate more extensively on the details of this. A bit more so, where I'm a bit more familiar with is the stuff that has been recently published, resulting from the observations from by IXPE of Vela pulsar wind nebula. Again, this is a very bright X-ray source, so this was obviously a very attractive target for IXPE to observe. And again, this is just basically very basic information about the system, that there is a large chunk of X-ray emission coming from Vela X, and this is basically I think it's probably coming from Rosat image. And then radio nebula is significantly smaller, is sort of within here, and the X-ray nebula is roughly comparable in size with the X-ray nebula. This is again the image of the 3 separate detectors that are stacked on top of each other. And again, the point spread function of XP is not fantastic. It's probably somewhat comparable to what it is for NuSTAR, maybe somewhat worse. All right, so the XP results from the Vela pulsar wind nebula are that, first of all, the polarization is averaged over the entire image. It's already quite strong. It's approximately, as you can see here, on the order of 45%. But it's actually stronger than that. It turns out that it's an imaging instrument, so it can provide you polarization information as a function of the position within the nebula. And it turns out that X-ray polarization is actually quite well aligned with what we see from the radio polarization. So again, this is an image of the nebula itself, and you can see in black to be the direction of polarization from the X-rays, and then the white lines are from 5 gigahertz radio polarization from this paper by Dodson et al. So this clearly indicates the fact that this is probably the same process of acceleration of particles in this pulsar wind nebula. Something I'm a bit more familiar with than the last 2 targets is blazars, of course. We've heard very nice presentation about blazars from Leah earlier on, so I will not go through a great deal of details, but they're active galaxies with jet pointing close to our line of sight. They're very variable in all bands, so this is where you really do need to have simultaneous and strictly simultaneous observations. And there are 2 general classes of those objects. And the reason why I'm sort of bringing the taxonomy is because the fact that the expected polarization level would be, polarization in general would be different in lower luminosity sources versus the high luminosity sources. The low luminosity objects, such as Markarian 421, which is a picture taken or figure taken from a paper by Mislav Balakovic, we expect, at least the theory before the convincing observation was that the entire broadband spectrum coming from radio all the way up to maybe about hard X-rays or so should be produced by synchrotron emission. The emission beyond that is probably inverse Compton of the by the same relativistic electrons that produce the synchrotron and using the same photons that were produced via synchrotron emission. So in the case of those low luminosity objects, we expect relatively high level of polarization to X-ray band, simply because of the fact that it was the same synchrotron emission that you infer from polarization in optical and radio. Presumably, one should expect a polarization as well. On the other hand, in the high luminosity sources, as the one on top here, this is 3C279 from a paper by Masaki Hayashida, you expect that the X-ray emission all the way up to gamma rays is probably already inverse Compton emission. So you expect significantly lower level of polarization in those sources. And in fact, you will see in a minute that this is basically what we are observing. So XP observation of Markarian 501 has been conducted over 100 kiloseconds, and that gives you a sense of the instrument sensitivity. If you need 100 kiloseconds for a source at the level of few times 10 to minus 10 to detect polarization 10% level, that gives you a sense of, what do you need to do for those brightest sources at least to be able to determine whether there is or there isn't polarization. So the important part here is that NuSTAR actually conducted very strictly simultaneous observation with XP and was very successful to provide the measurement of the broadband spectrum, which is actually not XP itself would have inferred the spectrum to be just a power law. It turns out that it's not quite a power law. We are in the case of Markarian 501, we are at the very peak. I don't think I have the spectrum here for this, but it looks very similar to Markarian 421, and XP is actually covering the very peak of the spectral energy distribution here. So this measurement with NuSTAR allows again the very broadband energy distribution, and the spectrum is not, as I mentioned, straight power law, but it looks like a log parabola. So it's gradually steepening, gradually softening spectrum going to higher energies, which has important implications on exactly where we are on the spectral energy distribution level. So this is, again, one of those plots where you can see the angle and the level of polarization. So this is the Q over intensity versus U over intensity. And again, the distance from the center is the level of polarization. And you can see that the polarization level here is on the order of 10% in two different observations. They're basically consistent with each other. So we don't see very clear indication of rotation of polarization angle here. But we feel that this is the confirmation of the fact that the X-ray emission is really indeed produced by synchrotron process. Now, there's more than that you can actually learn from this. You can actually learn a bit more about the acceleration process of the particles themselves. It turns out that you can have a variety of models that produce slightly different dependencies of polarization on the photon energy. So for instance, in a single zone, very simple model, that polarization should be constant as a function of photon energy, and so on and so forth. There's a variety of models here, but we actually see strong chromatic dependence on the polarization. Turns out that polarization level in the optical in this object is significantly lower than it is in the X-ray band. And that kind of dependent, the energy dependent level of polarization is something that's actually expected from basically energy stratified shocks. So we actually have this in this table on the left hand side as the most valuable, most appropriate models for this source, the most appropriate one. All right, and not all of our observations resulted in detection of polarization, even though we tried to select sources that were very likely to be polarized. A good example here is this very bright radio galaxy Centaurus A, which is probably or for many years, it was the brightest extragalactic AGN on a sky. It was actually already detected for many, many years by a variety of missions. It is unfortunately in these days going into slight decline. It's probably about a factor of 3 or so lower than it was when RXTE performed very long monitoring of this object. It was observed for also another about 100 kiloseconds or so. And again, paper was led by Stephen Ellard from Marshall Space Flight Center. And this is again an image of the 3 detectors together. There happens to be a ULX in the field of view that has not been fully analyzed yet. This paper again has been submitted and it's on the archives already. And here's the spectrum of the source. And we also have the level of polarization. So let me just jump to the next view graph here. The polarization level is not, the polarization is not detected in this source. And this is in fact, if you take a look on the spectrum here, the spectrum, basically this is essentially the same result as Felix Fürst had produced from NuSTAR. The spectrum is a very straight parallel with a clear indication of an iron line, but no Compton reflection in the spectrum. So this implies that probably most of the spectrum is actually produced in the relativistic jet rather than in the accretion flow onto the central black hole. There is this very prominent soft X-ray emission at the very lowest energy end, but this is most likely evidence of additional thermal component associated with the galaxy itself. The photon index is 1.88, so it's still rising in nu F nu. This is actually just counts rather than nu F nu. So that would mean that the X-ray spectrum is actually distinct from the low energy spectrum, which is, there is some polarization in it, which is produced presumably by synchrotron emission. So we believe that this is another yet argument supporting the result of Felix that the X-rays are produced by the inverse Compton emission. And again, you can see that this is simultaneous observation with NuSTAR, and the observation here for this particular source, where there's relatively little variability during the entire observation, gives us also another little bit of useful information with basically this cross calibration between the 2 instruments, which now we believe it's really in quite good shape. So so this basically is the again once again the indication that the polarization in the radio is significantly, it's about 1% in the near infrared, which is where the synchrotron is probably less diluted by some kind of more diffuse emissions, about 10%, and then there's no significant detection of polarization in the X-ray band. All right, so in a summary, XP was launched 6 months ago. It's doing very well, was launched successfully. Observations are continuing. There's probably on the order of 20-ish, if not more, maybe 30-ish sources in the can right now. And they're being analyzed. Not every single observation is easy to analyze simply because of the fact that there's still some little bits and pieces that of the data analysis that have to be worked out. So it's working with other observatories, and NuSTAR, most significantly for the variable sources, is providing very important constraints on the spectrum of the source, which in turn leads us to be able to understand the source geometry and emission mechanism in those sources more fruitfully. So this is all I have for my presentation. But if you want to take a look on the past and future observations, I think that those are all publicly available on the XP website. So I suspect that there probably will be a lot of collaboration going on between NuSTAR and XP in the future, simply because of the fact that the missions are really quite complementary and designed to focus on slightly different areas, but at the same time, combining the data from the 2 instruments together is going to be probably the most important next step for scientific observations. So something I want to mention is that there will be a number of observations coming up, so and number of results coming up. So keep your eyes on the papers to be published on archives. Among others, there will be active galactic nuclei, those radio quiet objects that will be published in the near future. There was a big effort trying to put together some of those papers. And again, X-ray binaries, you already have heard about Cygnus X-1 and so on and so forth. So this is very much the effort is really going on full time. So I'll stop here. Thank you.
Any questions?
So are there observations planned with IXPE to check some of the previous X-ray polarization measurements with different missions in the past, like with CRAB or?
That's a very good question. Yes, the CRAB is obviously one of the targets, and that's probably not a secret that the X-ray polarization level measured from the CRAB is actually consistent with previous observations. But that's the only one. As far as I know, there's no other X-ray polarization measurements in the past. Marty Weisskopf, who's the principal investigator of this instrument, is in fact the person who published the original X-ray polarization results from the Crab Nebula. So
there's also for Cygnus X-1, but the measurements are pretty much on the 1 sigma detection level.
Yeah, the measurements from Cygnus X-1, again, I'm not familiar with the reliability. I cannot assess myself. You're talking about the integral.
So there's also a mission. It was a balloon mission with by a group in Sweden.
Right.
And
Yeah.
the Astrosat NuSTAR campaign as well, which had.
Right. I simply don't know about the comparison between the Cygnus X-1 versus their result. Also, with Cygnus X-1, you have to be really careful. It is an object that can be in very different states, and therefore making any kind of conclusions that we are inconsistent with their previous observations, probably not all that important or robust statement, because of the fact that it would be very different. For CRAB, it's a standard, right? But not for anything else, but yeah.
There's a question in the Slack from Daniel Stern. He asked, when will the first IXPE GOB, and is IXPE discussing coordinated observations as per XMM+NuSTAR?
Sorry, maybe Daniel, if you could just, I didn't quite understand it, so maybe you can actually speak.
Yeah. Greg, that was amazing. Very exciting to see XP results coming out. I was just asking when the first GEO call will be for XP, and is XP talking about doing coordinated time with NuSTAR the way XMM has done with NuSTAR?
I don't know whether there was any discussion between Marty Weisskopf and Fiona. I suspect that that's sort of a bit beyond my decision level making. I think I have every reason to believe that there will be such discussion, because I think that there's plenty of opportunities for the two missions to work together. As far as the GEO program, I think that XP will be, if I understand correctly, also just like NuSTAR was, a 2-year mission where the targets are selected by the science team. And then beyond that, the expectation is they will go into GEO phase, something very similar. I think that NuSTAR was so successful in doing it that I think that it's just an obvious path to follow. That would be at least my guess. But I suspect that's probably being discussed. And I wouldn't be surprised if that came to be decided by the next senior review. That would be my guess.
Looking forward to it. And I also, maybe one thing Norbert didn't mention was the first open access to NuSTAR was actually through an XMM call, not through the NuSTAR first cycle.
Interesting.
So maybe we could do the same with XP. Thank you. I think there's another question on Slack by somebody else.
Yeah, Christine, would you like to ask yourself, or I can read?
Yes, sure. If you can hear me, thanks for the excellent talk. And I was just curious about how you calibrate the polarimetry instrument on board. So it's like for example, for spectroscopy, we have radioactive sources on board the instruments, or we look at the CRAB. But how do you do that for XP?
I think that we rely primarily on a calibration on the ground. This is actually not a trivial thing to do, because there is really no CRAB type object that would be standard candle on the sky for polarization.
Yeah.
So I think that one of the ways to calibrate it is to also look at targets that you don't expect any polarization from. For instance, clusters of galaxies, and verify that there's no polarization, because any kind of systematic effect will start showing up in a case like this.
Absolutely makes sense. Thank you.
Thank you. Let's thank all the speakers again. Thanks.
Okay, so welcome everyone to AGN Census Part 2, Obscured AGN. Here we've got 3 remote speakers and 2 in person. And we're going to start with an invited review from Claudio Ricci. So please take it away, Claudio.
Okay. Thanks a lot, George, and thanks a lot to the organizers for the invitation. My apologies, I'm not able to be there with you today. So I'm gonna give a review on nuclear obscuration in AGN from our hard X-ray perspective, highlighting some of the great work that's been done with NuSTAR in the past decade. But before this, I want to start with somehow of an historical perspective, showing you like how much our vision of the circunuclear material around AGN changed. We started in the 90s when things, we thought that most of the material around AGN was distributed as a sort of donut. And nowadays we know that this is actually a much more complicated cake with things like clumpiness and disk winds playing a very strong role. And so since we are talking about cakes, I take the occasion to say happy birthday, NuSTAR. And hopefully for the next birthday, Peter Burman can make a NuSTAR themed cake. So going back to our vision of unification and of obscuration around supermassive black holes, here you have the seminal review work from Schi Antonucci back in the 90s. And this is a more, on the right, you can see a more recent version of this. And again, here I think like one of the main points we understood over the past 1 or 2 decades is that things like clumpiness are extremely important, that the BLR could play a strong role in obscuring creating supermassive black holes, and also outflows that can be extremely important. Particular dusty outflows as those that are predicted by simulation. I'm showing here some hydrodynamical simulations from the group of Vada and collaborators. And here you can see the dust, you can see the sublimation region at the center, and you can see how this dust is pushed away also on the polar axis of the system. And this is the action of radiation pressure, which we know now it's extremely important. So in my talk, I'm gonna start talking about how we can use obscure radiation to understand better the circunuclear environments of AGN. And then I will go to reprocessed radiation, in particular focusing on many of the advancements that we have seen both in modeling and broadband X-ray data over the past years. So I'm going to start with X-ray obscuration. X-ray obscuration can be used in different ways. For example, we can look at AGN repeatedly, and from this we can learn something about how variable this obscuration is. This is something that can come easily from the X-ray spectrum. Depending on how many clouds and how thick these clouds are, we are going to see different imprints of the X-ray emission. And in particular, over the years, it's become evident that there are objects that go from an unobscured situation to a heavily obscured one, where mostly only reprocessed radiation is observed, as you can see here. And this has been the case for several objects. Probably the most famous is the prototypical changing obscuration AGN NGC 1365. This is an object that has been shown, as you can see here, to have very rapid variations of the line of sight column density. You can see the black and blue points here have column densities of a few times 10 to the 23. And then all of a sudden here between the first and the third observation, you can see that actually the column density increased very rapidly. And for this system in particular, we know nowadays that these variations can last even only a few hours. So we know now more than 30 AGN of this type. I think we will have a talk later on in this session about this in particular. And there are also a couple of posters that I recommend you to check out. One thing that I think it's really interesting about this variable obscuration is that over the years, it's become evident that this is not the putative torus, but it's actually the broadband region. And this is because the variations are too rapid to be ascribed to the dusty torus. And in particular, some objects have shown that the X-ray source, which is illustrated here as this blue circle, can be obscured by comets of this gas. And in particular, these comets can have a very dense center, which can reach column densities of 10 to the 24, and then a less dense tail, which is made of ionized radiation, ionized material, sorry. And this ionized material can actually leave imprints around the iron K alpha region. One thing in which NuSTAR has been really exceptional was in detecting variations due to very high column densities. And this was the case for NGC 1068. So this is a paper that was published a few years ago. There was recently another paper on this same object confirming these results. And what happens here is that, well, we know NGC 1068 is a heavily obscured system with column density higher, possibly than 10 to the 25. And this was the case in December 2012. But then in August 2014, NuSTAR detected a clear X-ray emission visible only above 15 keV. And this is because a clamp, possibly from the torus, with a column density of several times 10 to the 24, moved out the line of sight so that for the first time it was possible to see transmitted radiation in this object. And here, I don't need to convince you that NuSTAR has been exceptional because using any other X-ray satellite at lower energies, we wouldn't have seen any difference, as you can clearly see it here on 10 keV. So all this has shown us that actually the sky seen from the supermassive black hole is quite inhomogeneous. And probably both the broadline region and the torus are made of clumps that are moving and can give rise to these changes in line of sight column density. Another way in which we can use X-ray absorption to learn more about circumnuclear material is to use large samples to build a picture of the average environment of the AGN. And that is because if we think that our survey has a good completeness, or at least if we know quite well the selection function, then we can look at how many obscured sources there are. And this is going to give us a clear insight on how much of the sky of the AGN is being covered by this obscuring material. And this is something that's being done with hard X-ray selected AGN, because of course hard X-rays are extremely useful for this. And here I'm showing you SwiftBat and the NuSTAR serendipitous survey, which have both been very successful in detecting heavily obscured AGN. And there will be a talk, I think, about this after mine. NuSTAR has carried out several X-ray surveys. Here I'm showing on the left some early results from Fiona Harrison's paper, in which they showed that NuSTAR is able to actually resolve up to 40% of the cosmic X-ray background. Luca Zappacosta has used hard X-ray spectra of sources, in this case from the Cosmos field, to combine them with XMM spectra to basically get good constraints on the column density. And this is something that both these sort of studies that were not possible, or at least easy, before the launch of NuSTAR. And there have been also several other X-ray surveys that I think have moved forward the field quite a bit. One thing for which NuSTAR has been really exceptional is in understanding how much gas we have in the line of sight of the AGN, particularly for heavily obscured systems. And here I'm talking systems that have very little or no transmitted radiation able to reach the observer, such as the Cercinus galaxy and NGC 5643. Before NuSTAR, we had only very loose constraints on the NH. And particularly for the Compton thick AGN, this has been really important. And I think there will be several talks later about this by Marchesi and Greenwell. But combining all these X-ray observations, particularly using the good constraints on NH we got from NuSTAR, it's been possible to get an average picture of the obscurer of an AGN. And this is a very simplified picture, of course. But we know now that about 70% of the sky of the AGN is covered by material with column densities higher than 10 to the 22, and about 20–30% has column densities higher than 10 to the 24. So we know that we have got very good constraints now on the fraction of Compton thick sources. And this is something Peter Burman also discussed, finding results that I think are in rather good agreement with what found also for other surveys. One thing that's been clear for now over 40 years, the first paper on this was in 82 by Lawrence and Elvis, is that obscuration fuels the effect of the radiation produced by the AGN. And this is not a surprise because we know that there is feedback, and obviously the place closer to the accreting supermassive black hole is going to feel the effect of this feedback rather strongly. This has been shown by the many studies that have found that the absorbed AGN fraction actually decreases with the X-ray luminosity. And here again, I remind you that the absorbed AGN fraction, when we know well our selection function, or if our sample is complete, is a proxy of the covering factor of the obscuring material. So this plot is basically telling us that as one moves towards higher luminosities, less and less of the sky of the AGN is covered by this surrounding gas and dust. And an interesting fact is actually that this trend changes with redshift. In particular, people have been finding that at higher redshift, the fraction of obscured sources is larger. One thing that we found using hard X-ray selected sources is that the main driver of this relation is actually the Eddington ratio. And this was done using the bus sample, which includes good estimates on black hole mass and Eddington ratio at the time. This is the first data release for 400 objects. And we found that when one, so again, here you have the fraction of obscured sources, but this time against the Eddington ratio. And you can see that things are quite flat up to a certain value above which there is a very sharp decline. And the interesting thing here is that this decline corresponds to the expected Eddington limit for dusty gas. And that's because when gas is coupled with dust, and dust has a much larger cross-section than fully ionized gas, one can be effectively above the Eddington limit at few percent of the Eddington ratio. So this is consistent with the idea that actually is radiative feedback what is changing the shape of the environment of accreting supermassive black holes. And also what we found is that when one controls for the Eddington ratio, any dependence on the luminosity disappears, suggesting that indeed the Eddington ratio is the main parameter, at least for local AGN. So this has led us to come up with a radiation-regulated unification model, according to which at low Eddington ratio, most of the sky of the AGN is covered by gas and dust. And then at higher Eddington ratio, basically a lot of this obscuring material is pushed away, might become the polar dust we observe in the mid-infrared, and the covering factor shrinks, leaving basically only the bulk of Compton thick material on the equatorial plane of the system. So here is a depiction of this radiation-regulated unification model. So what we are saying is that besides the inclination angle, the probability of a source to be obscured is also a function of the Eddington ratio. And therefore, depending on the Eddington ratio, if the system is at low Eddington ratios, then you have a lot of gas around the object, and it's much harder to see to have an unobscured line of sight. But on the other hand, when the covering factor is lower, so most of the sky of the AGN is devoid of this absorbing material, it's much easier to see the AGN as an obscured. We have recently revisited this using the latest data release of BUS, which will be on a special issue, I think, in a few weeks, and which now contains 800 AGN. And we have found the results in very good agreement. And thanks to the larger statistics, we were actually able to divide sources depending on their column density and look at how the covering factor of the individual column density bin changes. So if we look at unobscured sources here on the top left, you'll see that there is a great increase as the Eddington ratio increases, and this is consistent with the fact that radiative feedback is extremely efficient in removing the obscuring material. Interestingly, such a trend is not observed in the range between 10 to the 21 and 10 to the 22. And this is probably because most of the obscuration in this region comes from the host galaxy and therefore is not affected by the Eddington ratio. At higher column densities, we see this decline that we saw for the old sample. And interestingly, even in the highest Coulomb density bin, and this is sort of unexpected because the effective Eddington limit scales with the Coulomb density, but it's been proposed by several recent theoretical studies that actually things like infrared radiation trapping can become extremely important already at a few percent of the Eddington ratio, even at very high Coulomb density. So this would explain this decline that we see even in the higher Coulomb density bin. And one thing that I found extremely interesting is that when we compare the covering factor and its relation with the Eddington ratio, as you can see in this plot, with the recent results from the Eddington ratio distribution function for as with BAT AGN from the paper of Tonino that came out a few months ago, you can see that actually the place where you have the break in the Eddington ratio distribution function corresponds to the place where the AGN transitions from having most of the sky obscured to having most of its sky devoid of obscuring material. And this might suggest us that when the AGN crosses this point, since less material is available, the time during which the AGN accrete is also lower, and therefore is harder to see AGN accreting at this higher Eddington ratio. Again, this is a picture that probably applies to low redshift AGN. At high redshift, the situation might be more complex. One thing for which I think NuSTAR has been exceptional has been the study of how other additional effects such as galaxy interaction can play a role in the evolution of the obscuring material. So this is something that has been proposed by theory many years ago. And here I have some recent simulations that show how the Coulomb density of the gas towards the center changes with the time during a merger. So here you have an early stage merger with two galaxies far away, in some case a little bit of tidal tails, but then things get really interesting when you get to close mergers or the final phases, because then the Coulomb density is expected to increase very much. And this is all ascribed to the fact that basically when you have the interaction of two or more galaxies, the tidal forces from the galaxies can deplete some of the angular momentum in the center, and therefore allowing the gas to go towards the supermassive black hole, and so obscuring it and filling it. So several studies have looked at NuSTAR observations of nearby galaxies in mergers, which might or might not contain AGN. And this, I must say, it's really like this was the first time this was possible in the hard X-ray band, because works done before with BAT were not able really to see much due to the lower sensitivity. So what was done here was that AGN in mergers were divided according to their merger stage, in early mergers and late mergers, and then the Coulomb density relation with this merger stage was studied, and this is something that has been done by several works. Dan Stern did some really interesting work in a similar direction for hot dogs at high redshift several years back. So what was found is that AGN in late mergers, according in agreement with the theoretical expectations, they tend to be much more obscured than AGN that are in isolated galaxies and in early mergers. And you can see this here very clearly. This is the cumulative distribution of the Coulomb density. And you can see how all the AGN in late mergers, they have Coulomb densities above 10 to the 23. So this is telling us that AGN in isolated galaxies and in mergers, they have different environments. AGN in isolated galaxies, they have this sort of anisotropic obscure, where you still have a line of sights that are free from absorption, while on the other hand, in the late stages of mergers, the AGN are in a cocoon of gas and dust. So this is telling us that the drivers of obscuration are not only the inclination and the Eddington ratio, but also the merger stage, in the case galaxies hosting AGN are found in mergers. And I think NuSTAR will certainly increase the number of parameters here, because I think there is still much space to discover. So I certainly look forward to the next 10 years of observations of nearby obscured AGN. So I'm going to now tell you a little bit about the reprocessed X-ray radiation and how it can provide a complementary look of the closed environments of supermassive black holes. I'm always talking about neutralish, let's say, material such as the BLR and dust located further away. So we have now quite a few models that can allow us to study this reprocessed radiation. I think the most commonly used nowadays is Boros, developed by Mislav. He gave a very nice talk about this yesterday. We also have models that we have also models that include clumpiness. And on top of this, there are several platforms of ray tracing that have allowed to include more complicated geometries. And one of those is the Monaco platform, which uses GEANT4, which is a tool that was originally developed by CERN to study particles in the accelerator. And with Stefan Paltani, we developed Reflex, which also allows to use different geometries. And actually, hopefully, let's say, I'm about to submit a paper because we have been including dust also in our simulations to make them more realistic. So these models can then be applied to broadband X-ray spectroscopy. And this is something that has been done by several people. Here I'm reporting an example by Mislav, but we heard a few talks about this yesterday, and there will be, I think, 1 or 2 talks about this today, also a few posters if you're curious. But the idea here is that by looking at the reprocessed radiation, one can get several important parameters of the circumnuclear material. Such as the line of sight column density here, the average torus or obscure column density, which is integrated. So it's basically the average NH that you have around the supermassive black hole, and then the covering factor that before I showed you we were using, we were getting from surveys. So this is very interesting because, of course, when one does it for a large number of objects, then it can be applied and can be used to study the evolution of this circumnuclear environment. Another approach that we have used is to exploit higher resolution observations carried out at other wavelengths and then incorporate them in an X-ray model. This is an example for the Cercinus galaxy. Here we recreated a model with an accretion disk, a broadline region, and then a flare disk and a hollow cone. And all the parameters were set either from high resolution interferometric observations for the dusty structure, so the hollow cone and the flare disk, or from knowledge that we had from other wavelengths, and this mostly for the BLR and the disk. And we found that actually this model can very nicely reproduce the NuSTAR and Chandra data. As I was mentioning, when one looks at the reprocessed X-ray radiation and does it for a large sample, then can study and compare the results with surveys. And this was done here by Zhao in 2020, which did something very smart. They applied the Boros model, but using as a constraint on the inclination angle, some modeling that was done of the narrow line region by previous studies. And this really reduces the degeneracies, and they were able to find a decline of the covering factor with the Eddington ratio not too different from what we see in surveys.
2 minutes.
Yeah. And also by studying reprocessed X-ray radiation of AGN mergers with NuSTAR, what's been found is that actually the covering factor is typically rather large. Here again, I'm showing you the covering factor versus the Eddington ratio. Those are the Swift-Bath AGN. And you can see that these mergers are a bit all over the place. And this particularly the late stage mergers, which are the red stars. And this is again consistent with the idea that basically the obscuration in this object is very different and potentially is located farther away from the supermassive black hole, and therefore the Eddington ratio would really lose its importance, and one would really need very high luminosities to get rid of this obscuring material. So I have here my summary. Hard X-rays are really a great probe of the circumnuclear environment of AGN. We have seen from studies carried out with NuSTAR, but also with other satellites, that absorption variability proves that indeed the environment of accreting supermassive black holes is very dynamic. hard X-ray surveys carried out with NuSTAR and BAT have allowed us to infer some of the typical properties of the obscuring material, and detailed studies of reprocessed X-ray radiation, particularly using NuSTAR. And again, here NuSTAR is fundamental because if we don't cover both the K-alpha line and the Compton hump, we really don't have hope to constrain some of these properties. But these studies and the development of more complex X-ray spectral models are really helping us to study and to better understand the AGN environment. So I want to conclude with a big thank you to NuSTAR, because it's been really a milestone and has helped us so much in the past 10 years to understand the closed environments of supermassive black holes. And I certainly look forward to the next 10 years. Thanks.
Thank you very much, Claudio. Do we have any questions? Brett Lehmer in the room.
Yeah, thanks. Very nice talk. Thank you. I apologize for this question because you may have said it, but the covering factor versus the inclination angle, are those well constrained independently? Are those degenerate with each other?
Yeah, so when we use surveys, what we do is to assume that basically you take a bunch of objects within a certain luminosity range, and this number of objects is large enough that you are assuming that you are probing different inclination angles. So each object is probing one inclination angle. So when you sample this space well enough, you are basically able to say, okay, the fraction of obscured sources is telling me what the covering factor is, because I've been probing a lot of random inclination angles. So I hope this answers your question.
Yeah, that makes sense. I have a little follow-up though. I mean, is there any reason to believe that this is completely scale invariant, such as like not dependent on the black hole mass?
It's possible that there are, that's why we do these studies with black hole mass and Eddington ratio, because this is really helps us to understand whether there are things changing. So we do not really see any difference in mass, and the only thing we see is actually this strong difference with the Eddington ratio. Yeah.
Okay, that's great. Thank you.
Thanks.
We have a question from Poshak on Slack. Lovely talk, he says. Do you think ULERGs like Markarian 231, Teng et al. Are intrinsically weak or heavily obscured? And then how many ULERGs are there in the BAS survey? Is the second question.
Yeah, so in the BAS survey, I can start with the second one. We have only a handful of ULERGs. There are not that many. Concerning Markarian 231, I think there have been discrepant explanations, but I think like the most accepted nowadays is that actually this is an intrinsically weak object. But I mean, this could still be because you have a lot of like heavily ionized material. It's accreting rather rapidly, if I remember correctly. So it could still be that you have like highly ionized obscuration, or basically free electrons, Compton scattering out some of the X-ray emission.
Thank you, Claudio. So if anyone has anything else they want to bring up with Claudio, I'm sure we'll be happy to discuss on Slack.
Thanks.
And we'll move on to the next speaker now. Oh, well, let's thank Claudio again quickly. Yeah. Claire, are you there and able to share your screen?
Hello, can you hear me?
Hi, yes, we can.
Perfect. Okay, so I'll just share my presentation. Okay.
Yeah, take it away.
Great, thank you. So my name is Claire Greenwell. I'm a PhD student at the University of Southampton, and my work is looking for unusual AGN in large surveys. And for this talk today, I'll talk about the NuSTAR angle on that. So why is it interesting and important to search for these rare obscured AGN? So a lot of AGN growth occurs under these highly obscured phases. So if we can find AGN with these conditions, that can give us some insight into AGN growth and evolution. But of course, this very obscuration makes it quite difficult to find them. So we need good selection techniques and a lot of data to start off with. and now why NuSTAR in particular is useful for these. So here is a broadband AGN spectrum with different contributions from different parts. And the bit that NuSTAR is looking at is, of course, the hard X-ray section here. So this contains bits of the reflection spectrum, bits directly from the corona, and a little bit of the soft excess. And this part of the spectrum looks quite different in obscured and unobscured AGN. So this section here. So you can see that the shape in an obscured AGN is quite sloped, but in an unobscured AGN, it's much flatter. And we can use that difference in shape to find likely candidates for obscured AGN. So to do that, we need a nice big source of X-ray data. So this is where the NuSTAR serendipitous source catalog comes into play. So this is a big work by Lazalka Clint that's, I think, on the very verge of submission at the moment. And this searches for NuSTAR detected sources that are not the targets for any observations. So they're in observation fields, but they're nothing to do with the science targets of those observations. And this builds on the 40-month catalogue that was from a few years ago with up-to-date observations. So this is more than 1,000 new hard X-ray sources. And if you want any more information, you can talk to George Lansbury at his poster. So we'll look at the sources from this that are most likely to be heavily obscured. So there's a lot of sources in this work, and in theory, you could spectrally extract and fit every single source if you had the time to find the most obscured sources. But for this work, we're going to use a shortcut to select the most probable heavily obscured objects. And for that, we'll use the band ratio. So recalling the shape of that obscured spectra, this uses the ratio of the hard, so the 8 to 24 keV flux, and the soft, the 3 to 8 keV flux, to give you an approximation of the apparent shape of the spectrum, which is, of course, a bit easier to do without fully extracting every source, and is in fact done in the catalogue already. So yes, a higher band ratio gives you a harder spectrum, means that it's more likely you're looking at an obscured source. So here we see all the objects from the 80-month catalogue that have redshifts. So we require in this case to have a redshift because it, of course, makes the fitting of the X-ray data a lot more likely to be accurate. The gaps of sources in this catalogue without redshifts are being filled in, so there'll be more and more sources coming up. But for the moment, we're restricting it to those. Below the line are the sources with low band ratios, and above the line are the higher band ratio ones. So these orange squares are the ones that we think are likely to be highly obscured. Any that have a star around them were in the 40-month version of this work. So George Lansbury in 2017 did the analogous one on the 40-month survey, and he found 8 sources, 4 of which are likely to be Compton thick. So you can see that a few of the ones that are in the 80-month sources are the same as those, but you can see these empty stars, and that's where there's either new data or the updated analysis has changed the band ratio significantly. But for this work, I'll include any that have new NuSTAR observations since the 40-month work was done. So anything that's got actual new information. So the first step is to check whether they are still detected. So we use a comparison between the source and background counts to check whether it is a true source detection. And we do this in several subbands of the NuSTAR range. All of the results that I'll include must be detected in at least the hard band, because that's how you get either a value or a lower limit above our threshold band ratio, which corresponds to approximately a Compton thick likely AGN. And actually a few of them are also detected at above 24 keV, which is relatively unusual because the NuSTAR response, the NuSTAR sensitivity drops off a bit as you get to the higher energies. So this is quite unusual and interesting already. So here's an example of one of them, just with the 3 bands separated out. So on the left is 3 to 8, then 8 to 24, which are both quite bright, 24 to 50. I don't know how well this will come out on the big screen, but there is, even by eye, quite clearly a source in that image. So this is a really good one that's detected across this whole wide range of energies. This one is a bit dimmer. So this one, I don't know if you can tell, but is only detected in the 8 to 24 keV bit, so the bit in the middle. It's not detected in the soft band, and it's not detected in the very hard band either. This is also included because you don't actually need a soft detection. It can drop out in that band and still be an interesting source for us. So we end up with these 16 sources that are above our band ratio threshold with new NuSTAR observations. 2 of them are not detected with this method that I just talked about. This doesn't mean that they're not real necessarily, it's just a slightly different method than that was used for the catalogue with a slightly different threshold. 5 of them have quite low counts, so we'll of course keep them in the analysis, but they're not really, they don't have enough data to do any detailed modelling on the spectra. One of them overlaps with a supernova remnant, which is very bright in the soft X-ray. So that needs, particularly in the soft X-ray, needs a lot of some detailed background modelling to make sure that we remove any effects from that. One source that seems to be variable has got several observations over different time periods, and I'll talk about that one a little bit later. And then 7 more that seem relatively useful and simple. Okay. So the last set of data that we'll look for is the soft X-ray data. So of course, to help constrain the parameters for the fits, it's useful to have some kind of soft X-ray data to go with our NuSTAR data. A very high proportion of the 80-month catalogue has soft X-ray coverage from some source. It doesn't necessarily mean detections, of course, but from our 8 sources, so this is the 7 plus that 1 variable one, 6 of them do have XMM observations. 1 of them has Chandra and 1 of them has Swift XRT. So for this, we have some soft X-ray data for each of them, which is very useful. And just as a summary image of our X-ray data, on the top row is the NuSTAR hardband, in the middle, the XMM, and on the bottom is Chandra. So the small circles are the soft X-ray coordinates, and the larger circles are the NuSTAR coordinates, with correspondingly larger uncertainty, but they're all consistent with being from the same source in those positions. And we can see by eye at least, and statistically, that there is a source in each of those soft telescope images to go with the NuSTAR. So when we move on to the results, as I said before, redshift is required for these sources. So each of them does have an optical spectrum. Some of these are from surveys like SDSS, but some of them are from dedicated follow-ups with telescopes just for this catalogue. So I've removed the 2 non-detections, but for the rest, most of them show only narrow lines. This isn't an AGN classification. This is from the catalogue, and it's purely based on a width threshold from the lines, but it's likely to be analogous to the AGN classification of them. And as we'd expect, we expect these to be obscured AGN, so we'd expect to mainly see narrow lines, which is indeed the case. But we can use this to inform, for example, if we choose the inclination angle in the fitting to reflect what we might see in the optical spectra as well. And for the couple that I've been able to do some classification on so far, they both lie solidly in the optical AGN region of the BPT diagram. So yeah, this makes them classified optically as AGN as well as X-ray AGN. We can also look at the optical images. So most of these are from pan-stars, except for this one, which is from DSS. The white circle is the NuSTAR coordinates, and the red and blue crosses are the likely infrared and optical counterpart coordinates. This is done with N-way matching by Clint in the catalogue. So it should be, yeah. So we can see that some of these appear to be, so yeah, Claudio in his review a bit earlier talked about early and late mergers, and some of these look like they might be interacting. They at least have nearby galaxies. I don't know if I'd say that they're in late mergers, probably more like early, but so far 3 of these 7 are possibly interacting, and in the previous one, Lansbury found that about half of them, 2 out of 4 of the Compton thick AGN were in major mergers. So I haven't separated my 7 sources into Compton thick and not Compton thick yet. So, and we can't directly compare those, but it does look so far like the numbers might be comparable. Okay, and now a little bit on the first results of the X-ray fitting. So this is still a work in progress, but here's some of the initial results. These ones are assuming just an absorbed power law. So the intrinsic coronal emission, just a power law absorbed by material between us and them. And this doesn't give a very good fit, especially when you include the soft data to many of these sources. I had to fix gamma, and it just even by eye isn't very good. So we quickly moved on to a more physical model. So Boris, which I think, Claudio mentioned in his talk as well. And this generally produces a much better fit for each of them. It implies that most of these, so 3 out of these 4 are Compton thick. The other one is almost Compton thick. This is still, like I said, this is only kind of the initial steps into it. So we might need some more detailed modeling, especially J2249 in the bottom right. Boris gives it a very high scattering fraction, which may be a little unlikely, but it's an indication that a lot of these sources are indeed Compton thick, as we were expecting. So now just a little bit about this variable source. So this one had in 2016 simultaneous or approximately simultaneous XMM and NuSTAR observations, and that's the spectrum you can see on the right. Then it had more XMM observations in 2018, and then in 2021, 3 more NuSTAR observations in quite quick succession. It's quite near an interesting variable source, so it just ends up getting a lot of these rapid observations, which is really nice and lucky for us, and a good side effect of it being in the Serendip catalog. So what I've done with this is 2 minutes left. Sure. What I've done with this is fit the 2016 data with Boris again, and then assume that the parameters stay the same except for the normalization for the later data. And so what you see is that the luminosity has increased by about half an order of magnitude. But when you consider how close these second 3 results are together, like of the order of a couple of the months, it is quite a quick rise in luminosity. So this is with the NH fixed. If I free it and try and refit them, it doesn't change it a lot. So I think it's more likely that it's an intrinsic luminosity rather than variable obscuration that we've got there. But it's still a nice, interesting source. So in summary, we have 13 new sources that are detected with unusually high band ratio values. We're expecting these to be highly obscured, and from the ones analysed so far, it does look like the majority are Compton thick. There'll be more detailed analysis coming, including with the rest of the sources. But here's just a quick illustration of what we've got. So including the 40-month sources, this is 21 probable highly obscured NuSTAR selected AGN. So this is 2 to 10 keV luminosity against redshift, and these orange diamonds are where we're starting to fill in some higher redshift but lower luminosity, lower observed luminosity, sorry, gaps. So that's all. Thank you for listening, and I'll take any questions.
Thank you very much, Claire. So any questions for Claire in the room? Okay, I'll ask one quickly. So in this final figure, are any of these new sources which seem to be going to higher redshifts than the previous kind of unambiguous Compton thick AGN identifications? So these 80-month sources you've analyzed, are any of those looking like robust Compton thick or greater than Compton thick AGN?
And so these 5 on the plot are the 4 that I showed here plus J2143. So yeah, this one is 23.8-ish. So they're all, and out of these it was, yeah, they're all almost 24 or slightly above 24. So yeah, I think so.
Okay, but some with bigger errors than others. Yeah.
Yes, absolutely. Yes.
I don't see any questions online. So if there's none others in the room, let's thank Claire again for a great talk. Yeah. So our next speaker is Stefano Marchesi, who will talk about the Clemson-INAF survey of Compton thick AGN.
Okay, thanks a lot, everyone. This is the first part of a 2-part talk, as you see, so we're also sharing the laptop. And in this first part, I will give a review on almost 5 years now of the Compton-Thick AGN project from the Clemson-INAF group. This is a project that I'm working on together with many collaborations that you see highlighted there, in particular Nuria Torres-Alba, that will talk just after me, Shuri Zhao, Marco Aiello, and a lot of grad students doing a great work. Andrea Luna Pizzetti is here with a poster. Dhruv Jyoti is also here with a poster. So if you have the chance to go and take a look at them, they're very good. So luckily, Claudio Ricci gave a very good review, so I don't have to convince you on the importance of studying heavily obscured AGN. They are an important part of the overall AGN population, in particular Compton-Thick AGN, so sources with a line of sight column density with larger than 10 to the 24 particles per square centimeter. They must be very numerous according to multiple AGN population synthesis models, from the oldest ones that you see there to the most recent one, like the Tonimanana one that you heard about yesterday. They should be up to 50% of the overall AGN population. But if we look at the local universe, only about 5 to 10% have been detected. If you take a blind sample, up to 10% of are Compton-Thick, so way below the expected number. To detect them in the high redshift, we can use instruments like Chandra or XMM Newton, because the most prominent part of the emission, the Compton amp, the reprocessed emission at 20-30 keV, moves in the energy range, is redshifted where we can see it, but in the local universe, we really need NuSTAR to study these sources. So the Clemson-INAF Compton-Thick AGN project developed this multi-observatory X-ray approach to get a complete census of the most heavily obscured AGN. So you see there BAT, Chandra, XMM, and of course, a key role is played by NuSTAR. So we have a web page that I just want to highlight. We have there the whole catalog that we use as a reference, the Palermo BAT catalog. There's a list of Compton-Thick AGN in the BAT sample that we keep updated. And if you find something that is missing, please let us know. And we also report the spectra available for everyone to use with the best fit models that we used in our analysis. So, as I said, we started from the Palermo 100-month BAT catalog, a survey of the whole sky between 15 and 150 kV in the hard X-ray. Therefore, we have about 1,000 AGN that are very bright, because this being a whole sky survey, it's very shallow in terms of flux limit. And this is the ideal sample for this reason to characterize bright nearby targets. And as mentioned by Mislav Balakovic yesterday, this BAT catalog is not unbiased, but is the least biased against obscuration. So ideal to study these particularly otherwise elusive sources. We started with the part of the work which does not include NuSTAR. The preliminary part was finding first determination of the line of sight column density for sources in the BAT catalog lacking of a soft X-ray counterpart. So we selected among those objects which still didn't have any information below 10 keV, objects which had the highest chance of being heavily obscured to maximize the efficiencies of our follow-up observations. In particular, we selected sources that are Cipher-2 galaxies based on the optical spectrum and then don't have ROSAT counterpart. ROSAT scans the sky, the whole sky in the soft X-rays between below 3 kV. And this means that if a source is detected by BAT and is not detected by ROSAT, it must be at least partially obscured, because the obscuration is energy dependent. Indeed, our follow-up across the years, a couple of papers with me as a first author, then a very recent paper published by Ross Silver, a graduate student in Clemson. We put together a sample of almost 30 sources. And indeed, as you can see in this plot where the line of sight column density is plotted against the redshift, almost 80% of them have an age above 10 to the 23. So this method is indeed very effective to detect sources, and we plan to expand it since BAT is continually scanning the sky and detecting new objects. As a reference, in a blind survey, only 30% of the sources have an age about 10 to the 23. So this is very good to find good candidate obscured AGN, but there are limitations to this approach, because as we know, the combination of Chandra and BAT doesn't make for a very good spectrum overall. These Chandra observations are snapshots of about 10 kiloseconds, so the count statistic is limited. So the parameters that we are able to measure, such as the spectral photon index for the AGN and the line of sight column density are very large uncertainties. And the other parameters that we are interested in, so the torus covering factor, the average column density, the inclination angle, are completely unconstrained. So we cannot have a complete picture of the geometry of this obscuring material. So we need an instrument that targets the 3 to 70 keV energy range, and I guess you may have some idea on which instrument we want to use is, of course, NuSTAR. NuSTAR is the perfect instrument for this type of studies, to study the Compton peak AGN with unprecedented statistics because of the effective area in the 5 to 50 keV. So just to give you an idea, this is an example of a spectrum of heavily obscured AGN with Chandra and BAT. If you add NuSTAR, the improvement is huge. Not only because you are filling the gap between the two observations, and so you can take into account possible flux variability effects, and so start to break the degeneracy between flux variability and line of sight column density variability, but also because in general you are able to track all the shape of the spectrum, improve the characterization of the spectral slope, the eye-roll line, the reflection component, and so on. So the first question that we had in our multi-year project was, if we add NuSTAR to our spectra, how does this change the knowledge on the torus properties? So we started analyzing archival data or sources for which we got proposal on single objects. The results have been published in a series of papers, a couple of works by Shuri Zhao, a recent paper by Alberto Traina, and also a work by Dhruv Sengupta, which is in preparation, and there's a poster here if you want to hear more details. Overall, it's about 45, actually exactly 45 Compton peak AGN in BAT with NuSTAR data. The sample is in the local universe with an average redshift of 0.03. And all these sources have soft X-ray counterpart, for the most part XMM, but also Swift XRT and Chandra. We fit our data with models like MyTorus and Borus and more recently UXClampy, which offer the best characterization of heavily obscured AGN. And what we measured in this first part is a systematic offset in the two main parameters, the photon index and the line of sight column density. A lot of sources that were classified as Compton peak based on the soft X-ray plus BAT, in particular those sources that only had Swift XRT data and therefore limited statistic, all had, you can see here, this is a plot of the photon index. On the y-axis is the photon index computed without NuSTAR, on the x-axis is with NuSTAR. The black solid line is the one-to-one trend. And you can see a lot of sources like above this trend. So the photon index without NuSTAR, it tends to be artificially soft. While if you add NuSTAR, you have a typical AGN value of around 1.8 with a sigma of 0.2. Since the photon index and the NH are correlated, the effect is that a lot of sources are reclassified from Compton thick to Compton thin. Again, here is a plot of, on the y-axis, the line of sight column density without NuSTAR, on the x-axis with NuSTAR. The Compton thick threshold are the blue dashed line, the black solid line is the one-to-one trend. A lot of sources that moved to the left are sources that have been reclassified. And these are, of course, implications also on the overall sample of AGN. Because in our work, we found that, particularly in the Marchesi et al. 2018 and 2019, we found that out of 35 sources that we classified, only 19 have been confirmed as Compton peak AGN when adding NuSTAR, so 54%. This, of course, has important effects also for AGN population synthesis models that are based, that include in their recipe also the observed Compton peak fraction in the local universe. Sorry. And a lot of sources have been reclassified with way lower line of sight column density. Just to give you an idea, the effect here, these are the confidence contours for line of sight column density on the y-axis against the photon index. These are those obtained without NuSTAR for one of the targets. One would expect, of course, these contours to shrink, but to collapse towards the center, while in reality, what happens is this effect of moving everything to the bottom left. So lower NH, lower photon index. So to move on, we then got time for a large NuSTAR program, a combination of 500 kiloseconds of NuSTAR and 250 kiloseconds of XMM to study the last 10 candidate Compton peak AGN in the BAT sample, still lacking NuSTAR data. The results of this work have been published in two recent papers by Nuria Torres-Alba and by Alberto Traina et al. both in 2021. And we obtained a lot of different results because we used then this data in combination with the previous one to get a complete statistical census of this population of heavily obscured AGN. So we got the most accurate measurement of the intrinsic Compton-Tick fraction in the local universe. In particular, redshift below 0.01, 20% of our sources are Compton-Tick. And this is an important result because it's in a very close agreement for the first time with the AGN population synthesis model predictions. We saw something similar in a Peter Burman talk yesterday on the Newland survey. And I want to remark that this 20% that you see here, this again, the intrinsic is the observed Compton-Tick AGN fraction as a fraction of redshift. In red is the number of objects in each bin, in blue is the cumulative one. In the lowest bin, our numbers go up to almost 28%, which is in close agreement with the prediction of the recent Tolima-Nannape model, if you take into account the flux limit achieved by Swift-Butt, which is for their model, the prediction is about, I think, 38%. So it seems that now we are really getting towards an unbiased sample, at least in the very narrow redshift, in a very narrow redshift bin. But you can also see that even Butt, which is probably the best instrument for this type of analysis, becomes very strongly biased once you go even only at redshift 0.02, 0.03. The second result that we obtained is that since we had this very high quality NuSTAR data, we were able to compute simultaneously the line of sight column density and the average torus column density. And this allowed us to see if the torus is more likely to be uniform or more likely to be clumpy. And we found that in the majority of the sources, there's a significant difference between the line of sight column density, which is responsible for the absorption of the photons at lower energy, with respect to the average torus column density, which is responsible for the intensity of the reprocessed emission that we see in the Compton amp at 20-30 kV. And this is shown in this plot. On the y-axis, you see the line of sight column density. On the x-axis, you see the average torus column density. The one-to-one relation is plotted as a red dashed line. This is a plot originally from Torres-Alba 21 paper and has been now updated in Semgut et al. In preparation. In a perfectly uniform torus case, you would see all sources lying on the one-to-one relation, but that's not the case. Indeed, it seems most sources tend to stay quite far away from this relation, which supports a scenario for which the torus is not uniform, but it's clumpy, a result that has been reported, of course, in several other works, but that we were able to validate in this systematic way, taking into account the X-ray spectra, and in particular, the effectiveness of NuSTAR to compute the average torus column density. And the last thing that we're working on, and we plan to submit by the end of the summer, is to get a sense of what's the space density and the X-ray luminosity function at redshift around 0 for Compton-Tick AGN, and use that as a reference for updating AGN population synthesis models. And finally, the last part. So the first two parts focused on single epoch observations, or in some cases on multi-epoch, in the sense that the soft X-ray was not simultaneous with the hard X-ray. This is a good approach, and I've shown you that we can achieve many interesting results. But if indeed the torus is not uniform, it's clumpy, we would expect that the line of sight column density should vary across different epochs, and therefore the best approach to characterize completely the obscuring material surrounding the accreting supermassive black hole is a multi-epoch campaign to study how the line of sight column density changes with time. And we find a way now to select sources that are promising in terms of being variable. And these are objects that I'm showing here in red. These are objects that are based on single epoch observations have a small covering factor and a large offset between the line of sight column density, which is significantly larger than the average torus column density. This means that these objects are likely to be to have been observed during an overdensity phase where we saw just through a cloud, but the average torus is much less dense. This means that we would expect to see variability on different time scales. To study this, we selected a source NGC 1358, which was found to be Compton-Tick by work by Shuri Zhao in 2019. And we got multiple NuSTAR and the XMM simultaneous observations on different time scales which allow us to prove different distances between the cloud passing by and the supermassive black hole. So two couple of results that we obtained. The first one is that indeed we found variability. The plot on the left is the line of sight column density as a function of time. You see the different shapes are different models. There's a general agreement between the models with some fluctuation, but the trend is clearly there. And we saw a very strong decline as we predicted. The source was Compton thick in 2017, and we found it to be going down to an H down to 7 10 to the 23 in January or February. And given the high data quality, we are also able to break the degeneracy between line of sight column density and luminosity, as is shown here in this plot on the right, where you see the confidence contour for the line of sight column density and the cross observation normally caused by variability in line of sight column density. So indeed, the source is very variable, and from this variability, we can get information on the distribution of the clouds, clouds that can be as close as a milliparsec or so, so very close and within the accretion disk itself. And the other important thing with which I want to conclude my talk is it has been shown from, for example, for works by Wisla Valokovic, and also you heard from Gonzalez Martino yesterday, single epoch observation can be affected by degeneracy between the primary and the reprocessed components, which makes it more difficult to measure the average properties of the torus and also properties like the luminosity and the line of sight column density in each epoch. With multiple epoch observation, we can break this degeneracy. We can assume that properties like the covering factor of the torus, the average torus column density, do not change on time scales of a few years. So we can fix them when we fit the data, and we can get much more accurate measurements. This is an example. On the y-axis is the covering factor, on the x-axis the average torus column density. In magenta, cyan, and blue, they are the covering factor computed for single epoch observations of NGC 1358. In black, you can see the contours when you fit together the three epochs. You can see that there's a huge refinement that allows us to break degeneracies. And on the other end, of course, to measure with even more precision line of sight column density and luminosity, which vary in each epoch. We are now working more on this multi-epoch approach, and you will hear from Nuria Torres-Alba in a minute, and also there's a poster from Andrea Luna Pizzetti. This is the summary of my work. This is a summary of the Clemson-INAF project. I hope I convinced you of the importance of NuSTAR, especially in joint agreement with XMM to study these heavily obscure sources, both with single epoch observations, and now we think the next step is multi-epoch monitoring to completely characterize these so far elusive objects. Thanks a lot for your attention.
Thank you, Stefano. Do we have any questions in the room? If not, then we have one on Slack from Serlen Baumann. And the question, well, comment.
Well, actually, I just
take it.
If you hear me, this is actually not a question. It was just a simple remark that when you were discussing in your talk on adding and not adding the NuSTAR, the power laws are softer when NuSTAR isn't there, and they're more flatter when the NuSTAR is added, and so forth. And I thought that like this is more of an AGN thing probably, because we observe the exactly opposite when dealing with CVs, actually non-magnetic CVs, and that those are galactic binaries, and adding basically just alone fitting the NuSTAR, they are steeper and they look softer. But when you have a much broader, particularly adding the softer components, they do with the NuSTAR, calibrating with the NuSTAR and the softer energies, the power laws were flatter. But not and what I'm trying to say, the alone NuSTAR gives a sort of a more the steeper, softer power law. So I thought that this is something probably has to do with the high absorption, that has to do with the observing the AGN thing and the Compton thickness, and that is more a characteristic that NuSTAR helps with getting a more correct power laws. But when you look into perhaps not high absorption and low absorption and thinner cases, not necessarily the NuSTAR alone cannot really calibrate well unless you really have some softer component, softer part that you can calibrate NuSTAR with. That's to do, I think, with thinness and rather than the high absorption. That's what this is a mere just a comment, I think.
Thank you.
Okay.
Great, thanks. Yeah, yes, of course, this is a bit limited to the results that we obtained with AGN, and as you said, is due to the way that the degeneracy between line of sight column density and photon index play. So it tends to go in that direction because by selection, we selected only heavily obscured AGN. So since the NH is overestimated, it has to be that the photon index is softer, but then it's also possible that there are some cases in which the other way around happens, although at that point you will have usually lower line of sight column density, and therefore the parameters are better constrained. But it's interesting that in other type of sources, there might be other scenarios. Thanks.
Okay, Claudio has a hand raised.
Yeah, just a very
Can you
quick
make it
question.
quite short, Claudio?
Yeah, very short. So nice work, Stefano. I was wondering, for the variable obscuration object, are you fixing the average column density of the torus and just leaving the line of sight free? Does that help?
Yes, that's correct. That's what we did. We considered that on time scales like this, we wouldn't expect a lot of variation, and this is what we did when using Borus. Then, of course, there are, when we use, for example, UX Clampy, we fixed the covering factor and the contribution of the extra reflector, so, and the photon index too. So the line of sight column density and the luminosity are the parameters that are allowed to vary between different epochs. We tried also leaving the NH torus free to vary. In general, the measurement of the line of sight column density are consistent with the uncertainties, but with the caveats that I discussed a bit. So we think this is the approach that we would like to pursue even for future observations.
Thanks.
Great. Let's thank Stefano again.
Thanks.
Our next speaker is Nuria Torres-Alba, who will talk about absorption variability in obscured AGN.
All right, perfect. All right, hello everyone. My name is Nuria Torres-Alba. I'm a postdoc at Clemson University, and I'm going to discuss the work that we are doing in characterizing the AGN torus in X-rays by using absorption variability in obscured AGN. So after the talks that we have had this morning, I hope that everyone's very convinced that we all know the torus is indeed patchy. We have seen occultation events in X-rays. We also need to use clumpy models in order to reproduce the SEV in the infrared. And this particular plot that Stefano showed shows that for the sample of obscured AGN that we have analyzed so far, when we are modeling the average torus column density and the line of sight column density, they do not match. In fact, they almost tend to avoid this one-to-one relation that I'm showing here in the diagonal line quite systematically. However, the line of sight column density is not a property of the AGN. It's not a property of the torus. It's a quantity that will vary with time as the torus rotates. Claudio Ricci showed a very nice image of the view of the sky from the AGN's point of view. As that torus rotates, we will always be observing the AGN from a different, through a different line of sight, right? So we're going to see a different quantity of NH in our line of sight. So this plot is susceptible to change because what we're showing as the line of sight NH is a value that will go up and down in this plot with time. And we are particularly interested in seeing how it does that and how it does so in relation to the average torus NH, right? So as I am showing here, the line of sight NH is the emission, comes from the emission emitted in the corona that gets to us in a straight up line and is affected solely by the quantity of NH in our line of sight when we are piercing through the torus.
torus is going to rotate, this is going to change. But the average NH comes from modeling accurately the reflection component. And the reflection is happening in all parts of the torus, either behind the AGN with respect to us or in front. And therefore, the NH that we measure is representative of an average value throughout the whole of the torus. And this is how these two components, which we call in here the transmitted power law and the reflected component, play out in the spectrum of an AGN, in the X-ray spectrum of an AGN. And in here we are showing in this GIF how the spectral shape changes very much as you increase the amount of NH in the line of sight. And at some point, the reflection component can even fully dominate the emission. So based on this, we're interested in finding sources in which we can model very well both the line of sight NH and the average NH in order to better understand the results that we saw in this figure original. And by the way, Dhruva Sengupta has an e-poster with an updated version of this figure. So what we are mostly interested in doing here is finding a sample in which we can find good sources to analyze in order to derive a good fit and a good quantity of the line of sight NH and the average torus column density. And we found the best parent sample in the work done by Zhao et al. In 2020, in which we analyzed a sample of 100 local but selected AGN. This means the sources are going to be very, very bright, therefore good data quality. And also the sources in this sample were all Compton thin. Compton thin sources are ideal to us because these are sources in which we are seeing both enough of the reflected component because they are moderately absorbed, but at the same time, we're still seeing the line of sight component because it's not completely absorbed. So we can model and obtain the good approximation for both quantities. Also, another important thing about the sources in this sample is that they all have at least one NuSTAR observation. And NuSTAR, as has been shown so far, is fundamental to try to get accurate values of the line of sight NH and the reflection component. The NuSTAR observations I am marking here in this simulated data, in which the only difference between one spectrum and the other is the line of sight NH. And it's particularly important that we have this data because the torus properties, as they change, they affect particularly the way the spectrum looks in this range, in the Compton hump, right? So for example, in here, somebody asked before how degenerate the properties such as the covering factor and the inclination angle are in these models. Well, when we are looking at one single source, they can be quite degenerate. So it's important to have good data and if possible, even multi-epoch data for sources in the NuSTAR range. And here I'm showing just how for Borus in particular, for the Borus model, the spectral shape can change when you have different covering factors from a very obscured source to a very thin torus, different inclination angles, a different average torus NH, and even different metallicities, although this is not something that we aim to model yet in this work. So this work performed by Shuri et al., he derived the torus properties using one NuSTAR observation and one soft X-ray observation, all from the archive. So the caveat of these is that these observations, being archival data, they're not going to be simultaneous, right? So in this plot that I'm showing here, we're not going to have this very nice data. We're only going to have, for example, the pink NuSTAR data and the dark blue XMM data. And they obviously do not match, right? In some cases when there is variability. So in fact, we saw that for 31 out of these 100 sources, we did need to introduce some sort of variability in order to be able to satisfactorily explain the X-ray spectrum. However, it is not trivial when you only have two observations to disentangle the intrinsic flux variability from the NH variability in the line of sight. Therefore, when we went through this sample again, we selected all 31 of these sources that showed, according to the best model by Zhao et al., either NH variability or intrinsic flux variability as potentially NH variable sources. And in fact, 18 out of these 31 sources had multiple additional archival data. And therefore, we thought this was an ideal sample to start studying and seeing how the line of sight NH can vary with time. So what we do for the source analysis, and this is related to what Claudio Ricci just asked Stefano, we are assuming when we simultaneously feed all the data that the reflection, the shape of the reflection component does not change, because we are assuming that it comes from the whole of the torus. It's representative of properties of the whole of the torus, and our data spans at most some 20 years, and we do not expect the shape of the torus to significantly change within these timescales. So when we are fitting a source, such as the one that I'm showing here, we are considering that there can be intrinsic flux variability, which is easier to see in the NuSTAR range because it's less affected by observation. We're also assuming there can be NH variability, and in this source in particular, we can see how the spectral shape in the 2 to 5 keV range is very, very different, and this is indicative of NH variability. However, the shape itself of the reflection component, we consider that it's constant, and it's this trick that allows us to place much tighter constraints into the fitting, both of the general torus properties and of the average NH and the line of sight NH at different epochs when compared to single epoch fittings. And so far, following this method, we have analyzed 14 sources with a total of 54 observations. And the results that I'm going to be showing today are going to look a bit like this. And it's easier to explain them like this because the real plots are actually a little bit more messy. So I'm going to be showing NH as a function of time, and each single data point is going to be a point at a single epoch of the line of sight NH. And I'm going to be comparing these values, first of all, between each other. If they are not compatible within errors, then we are seeing some variability. And I'm also going to compare them to the torus average NH, the best fit of which is shown with this dashed line, and the error range for it is going to be shown in these dashed regions. And based on qualitatively on how these plots look, we so far have classified our sources into having 3 main behaviors. The first of which is the actually non-variable sources. So 3 out of the 14 sources we have analyzed do not show NH variability with time. As always, when I say NH variability, I mean line of sight NH variability. Again, we consider that the average torus NH does not change. And interestingly enough, we see that all these sources that do not seem to vary in line of sight NH with time have a line of sight NH that is compatible with the average torus NH. This by itself is not surprising, but it becomes a bit more surprising after I will tell you the later results. In principle, if we are observing through the torus at different times, piercing different lines of sights, this torus keeps changing, and I always see the same line of sight NH. It's obvious that the average NH of the torus is going to be that one, right? So in this sense, this adds up, this matches. When you're looking at these plots, you will see that in here I'm showing 3 different models instead of 1. So I'm showing both my torus, Borus, and UX clumpy results, which makes them a little bit more messy to look at. Something that's interesting, however, is that the models almost always agree on the values of the line of sight NH and also on the average NH of the torus. So we have a consistency that we like. When we're looking at the variable sources, we see 2 different types of behaviors. One of them is the one I'm showing here, in which 2 out of the, of the 14 sources that are variable have a line of sight NH that is consistently below the average torus NH at all epochs. In fact, this particular source I'm showing here has been analyzed by Andrea Luna Pizzetti. She has a very nice poster right over there, and she can give you more details about the behavior of this particular subtype of sources. But the way we think they can be quite easily explained is by assuming that there is an inner reflector ring within the cloud distribution of the torus. This is an idea that was mentioned also yesterday, this torus within a torus, or this idea that perhaps the thinner region or the middle region of the torus is thicker than the rest of the torus. And this region is the one that may be mostly responsible for the reflection, while when it comes to obscuration, we're just piercing through the cloud distribution, and therefore this keeps changing with time. And it has a lower value because it's not as thick. And in fact, this is something that's considered as a possibility by the only clumpy model that we are using to model our sources, which is UX-clumpy. There's a possibility with that model to introduce an additional thick reflector, and it is in fact needed to explain some sources. And when it comes to our sample, only these two sources that are showing this behavior, only these two sources require this additional thick reflector in their center. So again, this so far adds up. Something that's perhaps a little bit more interesting is what we see that happens with the rest of our sample, the majority of our sample. 9 out of 14 sources show the exact opposite behavior. So when we are looking at the NH variability as a function of time, this always remains systematically above the average torus NH. Not only that, but this can be an order, even 2 orders of magnitude above the average torus NH, which is a surprising result to us. For example, I'm showing here that this is the nicest source that we have, the nicest data. And as you can see, there's an important variability in these sources. All of them, they do not match the average torus NH. The only ones that match the average torus NH were sources that were not showing variability. And again, for these sources, we did not need to include into UX-clumpy this additional thick reflector, which is consistent with the results of Borus and my torus that gives such a very thin column density that's responsible for the reflection. We are not truly sure why so many of our sources are behaving this way, why they have such a thin reflector when clearly the obscuration corresponds to a much higher column density. So here for some conclusions, I will just say that 11 out of the 14 sources that we analyzed turned out to be NH variable. This is not really surprising that there's such a large number because we selected this sample so that we could find NH variable sources. So we started from a biased point of view. This has not surprised us. However, our results do seem to hint at a physical separation between the obscurer and the reflector in the torus. The two materials do not seem to have the same density. In most cases, in fact, the material responsible for reflection is thinner than the material that's responsible for obscuration. Something that we still need to do so far is find a way to better quantify these results so that I don't need to show them in such a qualitative manner by quantifying how variable our sources actually are and how much different the average value of the line of sight NH that we see at different epochs is from the NH of the reflector. And then I'll just finally go into the additional work that's being done by our group into this project. As I said, Andrea Luna has a poster in which she does an in-depth study of one of these sources that's particularly interesting. Isaiah Cox, another one of my students at Clemson University, is developing a method to try and find NH variable sources, thank you, based only on a quick hardness ratio analysis so that we don't have to do this huge in-depth analysis for every single one of our sources. And finally, Dhruv Sengupta, who also has another poster here. With him, we're soon going to start working in more multi-wavelength based analysis, probably based on SED fitting, trying to find correlation between the SED of these sources and the behaviors that I have just shown for the different source populations. Thank you.
Thank you, Nuria. Any questions for Nuria? Would you like to use the microphone at the side?
Please forgive me for the very basic question, but I seem to have missed this. How exactly do you tell apart the line of sight column density from the average column density?
Yes, so if I go back here, right, the line of sight column density is something that is only going to affect one of the components of the X-ray spectrum. Okay, so part of the initial emission of the torus is going to get either absorbed by material in our line of sight or scattered away from our line of sight. And this is going to result here in this blue component that you see, which we're calling transmitted power law. If there's more and more material here in our line of sight, it's going down and down and down. Oh, I'm not showing anything.
Yeah.
No.
Someone else is changing things.
Can I? Okay, good. So this blue component here is going down and down and down, right? As we are increasing the amount of material in our line of sight. So see, we're starting with a lot of light, and as we go through the torus, we're losing this light away through absorption and scattering, Compton scattering away from our line of sight. And when it comes to the reflected component, which is a different component in the X-ray spectrum, this is coming from everywhere in the torus, right?
Okay.
So there's the light that gets scattered from other lines of sight can get reflected back to us.
Okay.
And this is going to create this purple component that you see here.
Okay.
Yes. And the key is that if we have good enough data, when we fit, we can disentangle between the contribution of these two components. So I am showing here. So in here, this dashed line is the reflection component in the spectrum. And the dotted lines, which are a bit harder to see and are closer to the data points, those are the line of sight components.
Okay.
So when we fit, and particularly this works very well with multi-epoch data, we need to find the shape of the reflection component that can explain the shape, the overall shape of the spectrum at all epochs when we add different line of sight components.
Okay.
This is how I do it.
Thank you. Okay, Peter Borman.
Thank you for the very nice talk. I was curious, what about multiple reflectors?
How about?
Multiple reflectors.
Multiple reflectors. This is certainly something that we could consider. What I have to say about that, though, is with the qualitative data that we have now, adding only these components can perfectly explain the data in the majority of sources. So I could, of course, add additional reflectors. I could make this reflector vary with time. I would be overfitting. I wouldn't be able to really say anything. The only thing I can say is that it's not necessary to fit the data to add any other component.
Do you think it could potentially explain the inversion that you see, the overdensity versus underdensity?
I think it's a possibility. I think it's a possibility that perhaps we are not yet good enough to disentangle a thick reflector and a thin reflector and the line of sight column density all in the same spectrum. Maybe we are only able to see a general, very curved component that the model is interpreting as all coming from the line of sight. And the only thing that is added, because it will have a very different shape, is a thin reflector. Because if you go back here to this data and you look at how the spectrum changes, with average Torres age changes, this lower curve that you see here in blue, that is for very low column densities of the reflector, so a thin reflector. And this has a very significant impact below like a 2-3 keV, in which we will not see the line of sight emission because it's been absorbed in there, right? While the others can get a lot more easily confused with the line of sight component. So I think it's still a possibility that we're only seeing the thin reflector in these sources, but there are additional thick reflectors that we cannot distinguish.
Great. For any other questions, could you move it on to Slack or, yeah. So thanks to Nuria again. A great talk. And we'll move swiftly on to the final speaker of this session, coming to us from a distance, is Jiang.
Hello everyone. My name is Jiang Jiachen, or just call me JJ if you want to. I am working at the University of Cambridge now, and I'm going to slightly change the style of the talks and focusing on only one object. So this AGN I will be talking about is a narrow-line one galaxy, but it has got some something special as indicated by the title. There's actually quite a lot of obscuration happening there along the line of sight. And if you're interested, you can actually scan the QR code here and check out this paper of mine. I just want to say this paper cannot be done without all of these amazing NuSTAR friends, especially Mislav, who very kindly computed some personalized models for me. To start the talk, I would like to take one step back and start with the unification model of AGN.
Jiang, can I stop you for 1 second?
Yeah.
For some reason, you're in full screen mode, but the right-hand part of the slide is cut off.
Oh.
So if you could just go back to non-full screen, that's probably better.
Is it
Yeah,
is it fine now?
there. Yeah.
Okay,
like
good.
that. Thank you.
Okay, good. I just want to, start with the unification model of AGN. The idea is very simple. So all types of AGN are intrinsically very similar. There are safer 1, safer 2, because they are viewed from different inclination angles. If there is a large inclination angle, we are looking through the torus. The torus blocks the broadline region behind it, so it shows no broadlines in the optical spectrum, and correspondingly, its X-rays from the innermost accretion region are obscured by the torus. So this is safer 2. An example of safer 2, optical and X-ray spectrum are shown in gray here. The safer 1 means you have a relatively smaller viewing angle, and we're able to see right into the broadline region. And consequently, you can see broad permitted lines in the optical band, and also in the X-ray band, we can see right into the central innermost accretion region. There are also some subclasses of safer 1 AGN, so narrow line safer 1 and broad line safer 1. The permitted line widths of narrow line safer 1s are usually narrower than those in broad line safer 1s, and narrow line safer 1s are often featured with a strong ion 2 emission and some high ionization emission line 2 in the optical band. So these narrow line safer 1s are believed to host arguably smaller supermassive black holes, accreting at a healthy fraction of the Eddington limit, sometimes around or even higher than the Eddington limit. So I'm showing you a sample study of a broadline safer 1 galaxies in red and narrow line safer 1 galaxies in blue in the X-ray band based on XMM Newton data. So each point here is 1 AGN, okay? And the average Eddington ratio for narrow line safer 1 is indeed higher than their broadline counterparts. There have also been independent studies showing that there's a correlation between the hard X-ray photon index and the Eddington ratio. So this is very similar here, and narrow line safer 1s are often found to be softer in the X-ray band than broadline safer 1s. Now I would like to show you some of the very extreme narrow line safer 1 galaxies in a sample I studied a couple of years ago. If you believe their black hole mass measurement in the literature, they're actually accreting at least around the Eddington limit, probably even as high as 10 times the Eddington. The gray dashed lines here in the figures are power law with a gamma equals 2.5, just for reference. So you can see that in the hard X-ray band above 2 or 3 keV, the hard power law is as steep as a gamma equals 2.5 or even steeper in a few of them. So this suggests they have a really high Eddington ratio. If you interpolate this power law to soft X-rays, you can see really strong soft excess emission. And there are quite a few models out there to explain soft excess, but it doesn't really matter what you believe. The evidence of soft excess emission means we are looking right into the central innermost accretion region, and there's not much obscuration happening along the line of sight. So far, so good, right? So this is all expected by the unification model. But we know it is called the unification model, which means it is probably wrong in some ways. For example, there are changing look AGN we heard of in previous days, and also classifications of safer 1 and safer 2 in the optical band. They don't really match their X-ray behaviors. There are also a lot of very weird intermediate type of AGN too. So now I would like to introduce one of the black sheep in the safer 1 family to you. It is called MRQ1239. So it is identified as a narrow line safer 1 AGN in optical band with a relatively smaller black hole mass of around 1 million solar masses. And to fit the X-ray data, one would need to start with an obscured power law with a line of sight column density of around a few times 10 to 23. And you will also need a scattered power law component too to fit the soft X-ray band. This was also confirmed by an even earlier XMM Newton data analyzed by Dirk Gruppa. There are indeed 2 X-ray light paths coming from this AGN. I won't talk too much about all of these very complicated soft X-ray emissions from this object, but only focus on the continuum modeling, okay, in this presentation. And Margaret has actually a poster and where she will present the latest XMM Newton NuSTAR observation we got for this object in 2021. Please go have a look and chat with her if you're interested. By fitting the spectrum with obscure power law, and you can actually see really strong and very pointy, narrow ion K-alpha emission line, and a huge Compton hump in the hard X-ray band. And to fit the data, you will also need the power law index to be at least 2.5. So let me just remind you what a typical disk ion line would look like. So these are the broad lines and the Compton hump in the NuSTAR spectrum of a black hole. Oops. Sorry, that was a fire alarm. I don't know what happens. I'm just gonna stay. Hopefully no fire. Anyway, so these are broadline lines and come down in the NuSTAR data of black hole X-ray binary and SIFO1 AGN, and they are all part of disk reflection. So there were quite a few talks in the past 2 days about disk reflection, so I won't talk too much about it. Anyway, this immediately tells us these narrow ion lines, MRK1239, are not from the innermost accretion region, but much, much further away. So based on the evidence of obscuration, the first option on the table for the model is of course, the torus model, right? In the paper, we focus on the Boris model. As you already heard from Omira, Mislav, Peter yesterday, the Boris model is a smooth, more spherical model, but it allows a variable E-cut parameter and a very high photon index as well. It also gives an option to investigate the inclination angle and the opening angle, which decides the covering factor of the torus independently. So I was joking with Peter Borman yesterday, you torus guys are just like too nice, too humble, and everyone is considering like 100 different torus model, and 99 out of them aren't even your own model or someone else's model. So I figured out I probably should do the same. So we actually show some tests with the my torus model in the paper, but the fit is much worse. Not much worse, it's worse, I would say, because the fit is packed at the hard limit of the photon index parameter in the my torus model. I didn't really try other models like clumping models, but it doesn't mean they won't work. I just want you to know that I still love you guys and you're still in my heart. And please let me just focus on the Boris model so far. Okay, let me just show you what the best fit Boris model here. I don't want to bother you with all the details. The most important direct power law continuum components are shown by the dashed dotted lines here. Okay, indeed, it shows a very soft power law in the hard X-ray band. This was confirmed by not only Suzaku data, but also the hard X-ray NuSTAR data, as gamma is as high as 2.6 in 2019 and 2.9 in 2007. So it was measured to be 2.92 by the XM Newton data in their group as a 2004 paper. However, it shows a huge difference in the soft X-ray band from a typical narrow SIFO1. So this power continuum from the corona is so obscured that some random emission from distance, maybe from the host galaxies, start showing up. And these are modeled by the collisionally ionized models shown by the shaded regions here. So in fact, the X-ray spectrum of this narrow SIFO1 looks like a SIFO2. Okay, but its intrinsic X-ray continuum is much softer than those in SIFO2s. For people who might not be very familiar with AGN, and SIFO2 AGN tend to have a low power law index of gamma less than 2 or 2.2-ish at most, I would say. So here is the gamma distribution of SIFO2 AGN sample in Mislav's paper. This is telling us that innermost accretion region in MRK1239 is actually more like those in high-end ratio narrow SIFO1 rather than typical SIFO2. So by fitting the spectrum with the Boris model, we can independently study the opening angle of the torus and the inclination angle. Although we cannot say they're identical, but they're actually quite consistent with a very low value, okay, suggesting that we're looking right through the edge of the torus, assuming this geometry in the Boris model. And if you link them in the fit, you can actually find the angle is around 20 to 30 degrees, around 26 degrees. So remember the really strong narrow ion line, the Compton hump I showed you earlier, one actually would need a very high average column density, around 10 to 25 to fit the data with the Boris model. If you consider the my torus model is a similar result of about 8 times 10 to 24 is needed. Okay, so to sum up, the average column density of this torus in MRK1239 is very high, but on the edge of the torus is only a few % of that. So it's probably not even Compton sick by some of your standards. So far, it might have already bored you. You may think, okay, this is just one bad example of a narrow SIFO1. Why do we care? and potentially some intermediate type in the unification picture of AGN. Our line of sight just passes the upper edge of the small opening angle torus in this object. But it is interesting not only because it has a small opening angle torus, but also because it has a high accuracy rate, while still it is obscured. Right? So here I would like to introduce a concept of effective adding limit. Claudio Ricci already mentioned this. So the adding ratio, the adding limit tells us when a gravitational pull cannot hold against the radiation pressure anymore. And if a luminosity goes above this limit, there would be mass outflowing. Okay, so the usual, the usual adding limit is calculated based on Thomson cross-section, as many of you already know. It's okay for the highly ionized gas in the innermost region, but when it comes to very dusty gas, like the ones in the torus, the cross-section is dominated by dust extinction, photon electron absorption, all of these different stuff. For example, if you're looking at column density at 10 to 23, for example, the effective adding limit is only 10%. It means you would need a luminosity that is 10% of adding limit to start blowing a dusty wind. So when the source is on the right side of the curve, a radiation pressure-driven outflow would form. And each of the points here is one AGN from the sweepback survey. You can see that most sources tend to avoid this region. So let's zoom in and see where MRQ-139 is. The black cross shows the average column density of the torus in MRQ-139. This is estimated mainly from the modeling of the reflection. From the torus, it's pretty high, consistent between two observations. The red and blue crosses are the line of sight column densities, changes a bit from 2 times 10 to 23 to 6 times 10 to 23. You can see that the average column density of a torus is pretty high. So the overall torus is heavy, it is safe, but the line of sight column density on the upper limit, the upper edge of the torus is in danger. It is right on the effective adding limit. Winds may be forming on the edge of the torus. So for your information, the gray dashed lines here are the adding ratio from previous literature. I don't want to spend too much time on them. If you trust them, the line of sight column density is definitely below the effective adding limit curve. I must admit that the average column density of the torus is very, very model dependent. The line of sight column density are, however, less dependent on the choice of the model. I just want to put it in content and show you where MRQ-139 is. It's basically the area almost no one else touches. I understand this is the X-ray conference, but I would like to put in a little bit infrared and optical flavors in it. So this is a near infrared spectrum of MRQ-139. The lower spectrum is ARK564. It's a typical narrow C41. It shows a typical near infrared spectrum. But if you look at MRQ-139, it shows this huge additional black body emission. According to the author, this corresponding to a temperature of 1,200 Kelvin. So it's really hot. And we're looking at a dust heated very close to sublimation temperature. And this dust is likely to be in a region of the torus or close to the broadline region that is being heated by the very high luminosity of the X-ray emission from the center. So shortly after we publish our work, a different group published a polarization study of this object. You can look at the polarization profile of H alpha and H beta. There seems to be some additional blue shifted emission components. There might be some winds happening there in the broadline region with a velocity around thousands of kilometers per second. I will leave you to justify whether you find their results significant or not. Okay, just to summarize. Okay, thank you. Yeah, our picture is very simple. It has this AGN has small black hole mass accreting around the ending limit. We're looking right through the upper edge and small opening angle torus. Intrinsic emission is very soft, just like what you would expect from a high ratio narrow C41. Overall, torus is heavy, safe from the radiation pressure, but the edge of the torus, we may have a wind. And it would be really cool if we can detect a blue shift ion absorption edge, for example, in the Athena or Crimson spectrum of this source. And so far, my conclusion has been based on this very good old torus picture, but as Mislav and a lot of other speakers reviewed and talked about yesterday and today, there might be clumpiness in the torus model. How can we investigate that with a fast variability in absorption, maybe? And we are also talking about highly accreting one here. So any X-ray wings or popped up disk could contribute to obscuration too. And how can we investigate that? Other possibility will surely require longer exposures and a higher spectral resolution. I think that's it. Thank you very much.
Thank you very much. We have a question from Peter.
do we know anything about the host galaxy in relation to, so you showed it's quite close to the blowout region on the effective Eddington limit diagram. So I was wondering how much of the obscuration could it be dominated by the host galaxy, for instance?
I actually don't know too much about the host galaxy. Yeah. But I guess the emission is probably completely dominated by the AGN, because the optical spectrum, at the least, is very dominant. It looks like a typical narrow line CP1. And in the X-ray band, yes. So Luigi Gallo had this paper talking about a soft X-ray emission, which I didn't really talk about. I focused on the AGN part. He had this idea that all of these random emission in the soft X-ray band could be from some very active starburst component. But obscuration from the host galaxy, I'm actually not quite sure. Yeah.
Okay, cool. Thanks.
Another question from the room, from Brett.
Yeah, thank you for the nice talk. I'm curious with the infrared data, since the picture itself is quite simple, is it not possible just to include this in the model? Or I'm sure you have to add additional components, but is there any advantage in terms of, finding some of these other parameters?
You mean add a model to add some parameter in the torus model and fit this?
Yeah.
I'm not an expert at infrared spectrum, sorry. But maybe I'm pretty sure someone in the audience knows about infrared emission from torus, because we heard about infrared talks yesterday about torus. So yeah, sorry, I actually don't know, but I would expect it could be easy. Yeah.
Okay, I don't think there's any other questions. I saw a hand raised and then lowered. Maybe someone answered their question already. So thanks again, Jiang, for a great talk.
Thank you.
And thanks again to all the speakers of the session, which was great.
So the rules are the same as they were the other days, which means you've got 1 minute, and I will be timing you, and I'll start clapping when that minute is up. So no mercy. Go ahead and start.
Yeah, hi. So I'm Rolf Ballhausen. I have a poster on EXO 2030, which was in a joint outburst last year. And this is pretty interesting. So just for example, there are as many as 3 potential cyclotron line claims reported in the literature. None of them are quite certain. We looked at this with NuSTAR and found a dramatic transition of the source over the course of the outburst in the pulse profile, in the hardness ratio, and consequently also in the spectral shape. So yeah, if you're curious to learn more, please come check out my poster. Also check out Philip's poster, also on the same source and outburst. They're both over there. Thank you.
So up next, yeah. When you're done talking, just slide it up. So I did not receive a slide from Buraiwala, and I don't know if he or she is here or online. Online. So unfortunately, I don't have a slide. If you are online and you want to just speak to your poster, please go ahead. Are you there? Sounds like not. Okay, so we're moving on to Jiang Chen.
Oh, hello everyone. So I'm Jiang Chen from ARMA project nowadays in Japan. So today I will show our recent work. So usually KPC scale AGN wind is considered as a signature of a powerful AGN activity. And we select a sample with the fastest outflow at the redshift lower than 2. But when we trace the central activity using NuSTAR, we found the non-detection even by NuSTAR's high sensitivity in hard X-ray band. So which suggests that so their AGN in the central AGN could be declined. So in this poster, I show the latest multi-band follow-up, including NuSTAR and also optical submillimeter observations. Thanks for your attention. And any discussion is welcome. Thank you. Yeah.
Thank you. I'm giving you guys a 10-second. Giving you a 10-second. Okay, next one. Go. Mr. Connor. What? Dr. Connor, I'm sorry.
Hello, everyone. I'm Thomas Connor from JPL and several other places. I'm here to talk about not any results, but an opportunity. NuSTAR is not the only telescope that's focusing hard X-ray photons. Chandra and XMM are also doing that. However, they're doing those when they've been redshifted to softer energy available. Basically, what I'd like to do is advertise to everyone here who are experts in hard energy observations that you can do a lot of great things at Redshift 6 and Redshift 7. And if you're interested in that, please talk to me. You can do things like look at super Eddington accretion, or measure high energy cutoffs, or look at blazars or obscured AGN. And you don't have to do anything complicated because you get 10 photons and you're very happy about that. And well, Axis is probably the one that many of you think would be the next place to continue on this. There's also a lot of opportunities for HexP that I think should also be considered. Thank you.
That's very generous of you. Next one up, Gonzalez.
Yes, hi, can everybody hear
Oh,
me?
you're online. That's correct.
Yeah.
Okay.
Can everyone hear me?
You're a little faint. Can you get
Okay,
closer to
so
your
if I speak a little
microphone?
louder, is it good?
Just speak louder. Please go ahead.
Okay. Hi, everyone. My name is Adam Gonzalez. I'm a postdoc at St. Mary's University in Halifax, Canada. So today I'm showing you some of our preliminary results where we analyzed 5 joint XMM plus NuSTAR observations of MR2251 minus 178 taken in 2015 and 2020. So here you can see that NuSTAR is crucial in revealing that the variability in this source is exclusively soft X-ray in nature. And you can see a constant power law shape over the 5 years. What we find is that the variability can be best described by 2 partial covering ionized absorbing zones that vary across all times, but most significantly in 2020. We use our best fit broadband spectral model to track the changes in color space of the Swift XRT observations that span the gap between the XMM plus NuSTAR observing epoch. What you can see is that there are 2 episodes of significant increases in the covering fraction of the absorbers over the 5 years. Please visit my poster or get in touch with me if you have any questions. Thanks for your attention.
Thank you. And next up, Eric. A little late, but.
So I think we all know that energetic pulsars produce a pulsar wind nebula, but after investigating for a few decades, I made this little plot here that shows that just trying to characterize the energetics versus the amount, how strong the pulsar wind nebula is by looking at the ratio of the flux from the pulsar wind nebula to the pulsar itself. And there's an interesting, there seems to be a cutoff. And I thought that, okay, this is great. There's some real interesting stuff going on. But then after a while, it turns out there's 3 examples that do not follow this. And so I've been trying to understand why that is, that these are, they have all this power, but no puff. So we see that examples here. And so my poster's over there. It's disappeared for some reason, but I'll put it back up.
Thank you. I'll get it. Okay. Next one up, please.
Hello, everyone. My name is Mikusincova. I'm a master student at Masaryk University, and I'm studying obscuration in AGN. So in my poster, I'm presenting a detailed study of NGC 3982, which was just until recently labeled as Compton thick AGN candidate. So I basically fit multiple models to the broadband spectrum, where all the models are assuming different and unique geometries. And despite this very large geometry-dependent degeneracies, all the models are in agreement that the SOR is Compton thick. Also, as the SOR is a low luminosity AGN, we cannot really, with the current data quality, we cannot really determine which geometry is the real one, the most realistic. But with the simulated IXPE spectra, I'm showing that actually with future probes like XP, we could really constrain the parameters of the geometries itself. Also, my poster is over there. Please, if you're interested, come and see me and see it, and you can find me as well. Thank you very much.
Thank you. And who've got next? Oh. You're not Leah.
No. So, hi everyone. I'm not Devang, but Devang couldn't be here today, so I'm presenting his poster on his behalf. Devang is a master's student from ISA Mohali, and he has studied a single source with many torus models, with including some new NuSTAR data. And on the left here, you can see the effect of using global parameter exploration with different torus models. But the key thing from his work is that this slightly new technique of sort of improving the runtime of nested sampling with step samplers appears to be able to dramatically increase the efficiency or decrease the runtime required for the fits. Also, he did some nice HEXP simulations to show that HEXP will be sensitive to micro changes in the obscura and much more sensitive flux limits as well. So if you're interested, the poster is at by the door over there. Yeah, come talk to me or reach out to Devang as well. So thank you.
Thank you. So the next one, I didn't have a slide for either, and that's Michael Parker. Are you online? Can someone confirm?
I think Michael is isolating in his hotel now.
Okay, hello. All right. So next one up then is, I can't actually read the name. Oh, here we go. Under Luna Pizzetti.
Hello, everyone. My name is Andrea Pizzetti. I'm a PhD student at Clemson University. So my study is on NGC 7479. So what we did is we performed simultaneous multi-epoch analysis on this nearby Compton thick AGN in NGC 7479 in order to characterize the torus geometry properties and the NH line of sight column density variability of the torus over time. To do so, we used 3 different physically motivated models, and although the spectra of this AGN is reflection dominated, as you can see in the tree plot in the center, the data quality allowed us to detect a variability in the line of sight column density, as you can see in the plot on the right. If you're interested to know more about that, please come and see me and my poster. It's there, is the black one. Thank you.
Thank you. So next up is Lenny, who is responsible for the vast majority of questions here today and the last 3 days. So Lenny, please go ahead.
Hello, I'm Lenny Sadi, and I'm a grad student at UCLA, and my poster is about searching for newly fading AGN in the 12-micron galaxy sample. So the 12-micron galaxies contain the most complete sample of nearby infrared bright AGN. So these are AGN that have strong mid-infrared emission from the torus. But out of them, 10 of the AGN show anomalously low O3 to X-ray to O3 luminosity ratio. So they have torus emission and narrow line emission, but they don't have much X-ray emission. And traditionally, this is thought to have been due to the AGN being heavily obscured, but it could also potentially be due to them being recently deactivated because the corona will shut off before the torus and narrow line emission do. So we observed these AGN with NuSTAR and found that while most of them were obscured, we found one, NGC 3627, that appears to be recently deactivated and is not detected by NuSTAR.
Oh, you're perfect. You're perfect on time. All right, and the very last one.
Hello, everyone. I'm Dhruva Jyoti Shengupta. You can call me Dhruvo. I work with Stefano Marchesi, Christian Vignali, and also with Clemson-INAF research group. This work has been mentioned in the last session by Nuria and Stefano, where we have selected 55 local Compton thick AGN candidates from volume limited sweetbat sample with archival NuSTAR data. And in the soft X-rays, we have used XMM Newton and Chandra. And for uniform torus models, we use MyTorus and Boros. And very interestingly, we found that using NuSTAR instead of sweetbat actually reduces the population of Compton thick AGN by almost half. You can see in the blue band and in the red band. So with this result, if your mind is blown and if you want to see my how we proceeded, you can check my poster in the digital format. But very interestingly, my poster is also getting obscured by another poster. So hope this technical problem gets solved soon. Thank you.
Thank you very much. Okay, that completes the lightning talks.